influenced by which factor. On Friday, we left with setting up the analysis pressure delay. So the trick we are using to delay the MOSH peaks to be eluted synchronized with the MOA chromatogram. And we see in the two chromatograms on the left side that we basically, it's not 100% perfect, but you might remember that our MOSH solvent peak normally ends here. We now managed to get it elongated up to here. Yeah, so we set a delay time of 3.4 minutes. That was what was set as last test on Friday, and you would basically set it to, let's say, 3.5 or 3.6. In the end, it's not that important because even in these conditions, you will see that, as we have learned, the end of the chromatogram isn't influenced anyway by this factor. And even when we would now measure alkanes on the back channel, we would see that the retention times in the beginning would be in the range of, let's say, 0.2 minutes, which is already perfectly fine. When you look into the SAT sheet, all specification regarding alkanes is only done on the end of the chromatogram, because influence on the beginning is too high, specific, especially when you have an HPLC pump, which might not be in 100% perfect shape, because as we have learned, the shape and the size of all the solvent stuff is all highly related on the performance of the HPLC pump. So do not spend so much time on optimization, especially for the solvent delay, because you can imagine now you would try 3.5 minutes, 3.6 minutes, 3.7 minutes, and when you would run all the 30 minutes for each of the tests, it's 3 hours later. Yeah, so do not spend so much time on this, because even in this condition you would perfectly pass all FAT, and even from the analytical point of view, as the peaks will be just different in a time frame, let's say 0.2 minutes. Let's just think about why this is important or why this is not important. As we have learned, all of these detention time markers are used for the cuts during the quantitation of the chromatogram. That's what I had in the slides. In here. So we are basically taking the times of these peaks to find out these cuts. In the beginning of a chromatogram, this is now again Gravex and SN500 as a second term, but typically when you look in real life chromatograms, typically this area here in the front of the chromatogram from C10 to 16, that's basically more or less empty. There is nothing that needs to be integrated, because the beginning of the chromatogram, as the column is separating according to the boiling points, this is the lightest compounds, which basically means compounds with very low boiling points. And when you have food, which is not just 1 day old, but a little bit older, means all compounds with a light boiling point will just start to evaporate, which is one of the easiest explanation why the beginning of the chromatogram is very often plain and without any contamination. Therefore, even when there would be a shift in the retention times, it doesn't matter, because there's nothing you need to integrate. Does this make sense for you? Okay. So basically, we have now managed to get from this scenario, where we have two distinct solvent peaks, to a scenario where we have, in this case, of course, it's for the slides, I try to get it really, really nice, but it's basically the same you are seeing there. If you could just for comparison, can you just close this chromatogram and take the one before? Just anyone. It's not this important. And then zoom out to the top so that we see also all of the solvent stuff. I don't know how often you need to click on minus for that. So it's basically ignore for now this thing here, but let's just pretend for the moment it's just perfect rectangular shape. I will talk about this. I don't know if we do this today, but and we have already talked about this shape here, which is coming from two squeezed tension gaps. But let's just pretend it looks like perfect rectangles. When you now do an overlay with the last chromatogram.
Can join teams.
Who is controlling the
Actually, join teams.
Can join teams and
Yourself.
show your screen instead. Anton is joining online if you want to see.
So he never appeared here.
No, you need to join team.
I need to. How to do that? Share.
Share the screen. Then after you will remove that.
Sorry, the wrong. Maybe of this maximize show.
Can you just have to minimize it? Yeah.
It is like overlap.
Yeah. Take the last one as an overlay, and that's basically what we have done now. Is, as I said, unfortunately the FAT is limited at, I don't know how much this is, 280 billion. I don't know. When you see now on the shape of the red chromatogram, this is what I painted on Friday on the whiteboard. That we are using the solvent which is parked or doing our stopped flow technique. We are using this solvent to get it's the blue one. Sorry. This is the reverse one. I did not want to have that.
Okay.
These chromatograms are not ordered as the injection order, right? Or I think you need to take 5.
So you want to select that one? Yes.
Yeah. Okay. Yeah.
Which one you want me to highlight first?
Blue one.
Blue one.
Yeah, so you can only highlight that for a second, so it will turn back in the same state as before. So you cannot highlight that for a longer period of time. We have, when you compare black to blue, you're seeing that we do not have an ending of the solvent peak here anymore at 4 point whatever minutes, but we are elongating the solvent stay inside the columns by turning off the gas flow. So we will have a little bit of solvent burned in the FID. Then, due to stopping of the flow, it will go down because less solvent or less solvent vapor. It is not liquid solvent. It's of course all the solvent vapor. Less is reaching the FID and is burned. Somewhere in the system, and at this point we are reactivating the gas flow, pushing everything out of the system. I did one mistake on Friday. when it comes to which time difference we are using. It's not from here to here, but it's from here to here. You know that you have made a suggestion on Friday which time is used for the time difference. It's not the end of the solvent peak to the end of the solvent peak, but it's the beginning of the solvent peak to the end of the solvent peak. And when you take this difference, it's much nearer at around 4 minutes. And you know that we have just learned we need a time more or less than 4 minutes. It's not the end of the MOSH solvent to the end of the Mohr solvent band, but the beginning of that. Because at this time, we are stopping the flow, or we are setting the flow to 0. So we need to use this time span to calculate the number, to get a first estimation how long to set the solvent delay.
I see the same, the beginning to the end plus 1 minute.
I think the plus 1 minute was what I said my mistake, because on Friday I did not realize that it's not this time here where we need to start, but it's basically this time to that time. Please ignore the stuff with the 1 minute. Okay.
The middle instead of the bottom, the same. Should we, if the chromatogram is elongated, then we should distinct from the bottom down.
As I said, unfortunately, this part here is originating from the retention gap because it's too screwed or too squeezed. In a perfect scenario, you would have a straight line down to the bottom. So in the end, as I said, this is only a very rough first estimation. My recommendation would be just start on 3.4 because that's the default value in the method, and just have a look how it looks like. Because difference from that number essentially also tells you a little bit more when it comes to troubleshooting. When the number gets far bigger than that, let's say 4 minutes, 4.5 minutes, or 5 minutes, it's basically you need to have somewhere a leak. Yeah, because you are just playing on some solvent peaks that are not in the way as they are expected. I have seen crazy numbers in there because people just wanted to have the solvent peaks on the same end, but they did not realize that it was basically something before that causing that you need this very big numbers. Like, for instance, easiest scenario is you have a customer not knowing about this technique with a very thin MOSH solvent peak, let's say only 1 minute small. Of course, by extending the delay time, even this can be elongated up to 7 minutes. But in the end, you are still losing all of your volatile compounds. So very important, and the most important lesson learned here, whenever you are looking or whenever you want to look on the MOSH solvent peak, you need to turn off the delay time. Otherwise, what you are seeing there is a combination of many factors, and you cannot see if you have enough solvent to retain all your volatile compounds. So that's basically what many customers are not understanding or are ignoring. They are just looking on the length of the solvent peak. They are setting it somehow to, let's say, 7 minutes, and they are still wondering why they not see all the standards of MOSH from the beginning of the MOSH.
Did you ever encounter a scenario where incorrect solvent weight or the amount of solvent left in the retention gap affecting the resolution of early eluting peaks?
Yeah. When you have too much solvent inside, the early eluting peaks exactly as you can see here. Look at the time difference between these two alkanes. These are exactly the same two alkanes. You see that they are thinner peaks, but their time the type difference, meaning the resolution, is much smaller. So when you have peaks like psi and C13 or 1 and 2 methylnaphthalene, of course they will start to pollute when you have too much solvent inside the system. What basically means your solvent band is very likely bigger than 2.5 minutes. So as I said, just try to be in the range of 2.2 to 2.5 minutes. Of course, it's easier when you are on the 2.2 minute side, because the more solvent left or the wider the solvent band, the worse is the resolution between those two peaks or two peak pairs.
In terms of helium and hydrogen, this resolution shouldn't be affected much, right?
When I look on the Van Dien plot, effectively it should even be better when you use helium, because the slope, or let's say the minimum of the curve for helium is a little bit better than for hydrogen. Means it should be easier to separate them using helium compared to hydrogen. But basically not a big thing. It can be troublesome when we're using allox. Then, but it's just basically psi and C13, but still at a stage where you can properly integrate the psi. But yeah, when this gets too broad, either that or that, when it's getting too broad, these peaks will start to pollute. Especially, they should not be, the solvent band should not be higher than 8 minutes, because at 8 minutes we are starting to heat up our GC oven. And then, of course, when you are starting to heat up, everything gets even more complicated. So the solvent should be out of the instrument before 8 minutes to be on the safe side, and that is no problem when you have a solvent bandwidth of 2.2, 2.5 minutes. We can, just to have a look on that, when you want to close the chromatogram, I saw that you have also measured the reverse ones, just to see at which stage this optimization was. Yeah, as you can see, the same numbers. I think we will more or less took the same numbers also for reverse. That's basically not working here. You see that the black trace, which is now more, is too thin, while our 3.4 minutes basically could be already too much on this one. Or let's say this is fine, and you just need to elongate that until that stage. So it's unfortunately, when you have squeezed detention gaps, we have two factors influencing each other. We have learned when the detention gap is squeezed that we have lower evaporation rate at a set pressure. But when you are trying to evaporate more, because of the PCM inside, you need less high evaporation pressure to reach your 2.2 to 2.5 minute solvent bandwidth. So just what I want to say is the numbers you are getting for normal injection, like let's say 100 kilopascal and 90 kilopascal for washing more. It's not really the case that this will be exactly the same. It could be even depending on the squeezing state of your system, that you will see very, very different numbers for reverse injection. The one of you set up 92 and 97. Was there an idea behind why you have flipped the numbers?
Just started to.
Because I don't know if that was maybe your intention. You do not need to flip anything. So Kronos is flipping this automatically for for you. Wash in reverse means this pressure is used on the second column. You do not just be a stupid customer, okay? You do not need to be smarter than we compare.
Okay.
Yeah. When there is here stated wash, you are talking about wash, not on first column, second column, whatever. This is done completely automated by the software.
Oh.
So wash in this case is the first FID. Wash in this case is the second FID.
So we should be big.
So we like to
Would be when the retention gets because you have managed to crash from us.
Wow.
This is a known bug. They know where it comes from, so don't be too afraid. But this would have been a nice case where you could send a bug report to our programmers, where you do not just quickly click on don't send. You could have sent this to our IT department, which is always nice when you get also this information. Because we will learn later, customers just tend to make a screenshot, and you are just getting one screenshot, maybe just one sentence in a mail, something like my system doesn't do what I want, with a bad screenshot, maybe even taken by your phone, so not even from the computer. And you can imagine that it's quite hard when you get 20 mails per day just with a bad screenshot and only one sentence. Then it's impossible to answer those emails. Yeah, when you was here on parameters. Yeah, so in fact, when both retention gaps would be exactly the same, you would have 97, 92, 97, 92. Okay. But when we would compare just the same retention gap, which means, let's say we want to go clean our only on the front retention gap, which means wash in this case, but more in the other case. It can be perfectly the case that you have course, then it means this number, because this is pure hexane, needs to be higher than this number, because this is like chromate, or let's say 30% like chromate. But comparing to that number, it would be that the difference between these is another one that compared to this number to that number. It's all unfortunately becomes very complex also in thinking about it when you are over tightening your columns. Because as I said, we are GC because of the gas nature. The gas compresses very number can decompress very much, changing our flow rate to a very high degree. Therefore, when we'll talk about this in a minute, when we are installing the extension gates, very in all columns. As I said, only that much force that is needed, not as much force as we can apply it.
So, Marco, so by right, the delay will need to optimize once
Yeah.
or
Yeah.
normal and reverse. It should be works, right?
Exactly, because the idea is to optimize everything to, let's say, 2.2 minutes, and then the delay needs to be the same. If it is not the same, basically it means something is very, very not okay on your system. It would be possible, even in this case, to apply a delay, but I wanted to have even this amount of numbers is already too much for many customers. But I would now add also an analysis pressure for reverse mode that needs to be also optimized, which could be done in the software, but basically another parameter that can be changed.
So it is trying, let's say I run the reverse, then even put 3.4 delay, then the server is a little bit far from the terminal is fine, right?
It's fine.
Just put 3.5 here.
Yeah. Okay. Regarding this topic, any open or left questions, or is at least the procedure, how we are doing it? I think it's all summarized on this slide here. Or is this clear in which order things should be done? To be always in the end, when you are following this order, you will have a system that is exactly set up in the way we need to have it. I just want to emphasize that it's not the only way how it can be done, because as you have also said by yourself, Mr. Tu is it doing another way. Also, a few of our service engineers are not following this way. But in the end, when the result is okay, the way is not really important. But if you are very new to all of that, that's a procedure where I can guarantee that when you follow from the start to the end, you will get to a proper result. Okay, so we have finished now this part. And I think I need to share again. And now that we have at least got a little bit of a basic understanding what is Moshmoa, how it is in general, how it is quantified, how our chromatograms look like, I want to introduce you in the used hardware for that. So which parts we are using to obtain what we have seen in the chromatograms. Somebody's changing GC.
Yeah, that's mine.
GC cylinders. How do you change it while all your GCs are burning FIDs, or do you have a second?
Yes.
Yeah, we have a dual.
Okay. Yeah, we have the same. So what we will talk about basically is what parts we have in the system. What parts are needed for the special options we are offering. At the moment, we do not need to understand the chemistry behind all that. It's only now, let's say, we are going through the parts we will then later have a look on in the instrument. So for the ones that have never seen it, that we can see it first in the slides, and then we can look on it in real life on the instrument. We basically start, this is mandatory when we just want to have a basic instrument. Of course, we need some kind of HPLC pump. And since we are using hexane dichloromethane, we need somehow to manage to provide a gradient formation. We need to do this with the binary pump because we are running a very fast gradient. This is what I've meant here with high pressure gradient formation. For the ones aware of HPLC or not aware, we have seen that on the pump last week. You have two basic ideas. High pressure gradient formation, you have two pumps, you are mixing it together with a T connector going to your HPLC pump, or the cheaper solution would be a so-called quaternary pump with low pressure gradient formation. But low pressure gradient formation always has a problem that it can only do slow gradients. This is too slow for the Moshmoa separation, and the consequence on the chromatograms would be that you would have from injection to injection very much movement of your Moa fraction. We have learned MOSH is not effective because it's diluted in the void time. Moa, because it needs the fast gradient formation, is only having stable retention times when you have a very precise, very reproducible gradient formation. This, unfortunately, is not the case on low pressure gradient formation. Therefore, we are using the LC40B. To be honest, no idea why we are using the XR, because the XR is more expensive than the version without XR. From the pressure point of view, it's not needed, because we are staying, as we have learned, in the range maximum 215 bars on the quaternary pump. On the binary pump, it's even only 120 maybe. So whenever you want to spare a little bit of money, you could even use the version without XR. That's perfectly fine. The only difference that matters is that the XR version is using other type of plunger sealings compared to the version without XR. And as you know, this type of version is using the black sealings, and this type of version with the XR is using the yellow sealings. And the yellow sealings are made of PE, so polyethylene, while the black ones is some kind of a PTFE composite. And we know that the PE sealings work more reliably than the PTFE sealings. Therefore, even this pump, when we get it in factory during setting up the instruments, we are removing the black sealings and replacing them against the yellow ones, because the PE sealings are better suited for normal phase HPLC. That's honestly, it's not a claim from Shimatsu headquarters. That's what we have seen comparing the instrument configuration to other vendors. So PE is better suited for hexane compared to PTFE. It's a little bit related. You might remember we have a lot of problems with electrostatics, and PTFE moving on a sapphire piston is creating more electrostatic than PE. That's one of the basic things. Additionally, we have, let's say, the cheapest version of a UV detector, the SPD40, and we basically do everything we can to have the HPLC part ready to be used for normal phase. This includes the sealings, and we have talked about that last week, also the optimized check valves. All the stuff with electrostatics and silicon carbide balls and all this stuff. Okay. Everything on the HPLC side is connected with stainless steel capillaries wherever it looks nice, and it's 0.13 millimeters inner diameter. This is normally a red colored capillary. So when you have red sleeves on your stainless steel capillary, or also peak tubing, when it is colored red, it has an inner diameter of 0.13. The color tells you inner diameter. You might ask why we are not using peak everywhere in the instrument. One reason is colored peak has a problem that the color is dissolvable in dichloromethane, which means you will have additional peaks in your GC chromatogram. When you use natural peak, perfectly fine. So you could use natural colored peak, which has this brown color, can be used also for the tubings. You might now again ask why we are not using it, because it would be more, let's say, user-friendly. It doesn't look that nice, because you cannot do sharp bendings in it. Peak, of course, is a polymer, and it's very difficult. You need to heat it up when you want to have sharp bendings. And also stainless steel has the advantage it can carry the weight of the columns. So basically, that's the very only reason why we are using stainless steel. It's not needed for the applications. Peak would be fine. So natural peak. But we decided for stainless steel because let's say it looks more expensive. it just looked nicer. I don't know how it's here for customers, but at least in Europe, it also comes to, let's say, some visual stuff on an instrument. I don't know how it's here. When it comes to connections and the nuts and the ferrules we are using, everything sold by Vichy is using the Balco connection system, connecting of a nut and a one piece ferrule. The Shimatsu connections normally have the ferrule is a little bit differently shaped than the Vichy ferrules. And when you want to have the lowest possible void volume, you need always to use the correct fitting on the correct connection. Does that make sense for you? For the ones that are not aware, basically comes to the following problem. You have a connection where you have a thread. On the bottom you have, no, that's not correct. On the bottom you have your solvent. So this is now basically the inner shape of a port, either on the HPLC pump or on one of the valves on the PAL. We have now a screw which fits into this thread, and you can now imagine when you have a tubing. No, let's do this another way. This is our port, so our liquid flows in here. So this is not correct. This is our port inside a valve or on the HPLC pump. We have our tubing, which always needs to be pushed onto the very end. So this is our stainless steel tubing, and our ferrule and the nut is sitting. The nut is basically this part here, and our ferrule is in front of that. And the sealing inside all of that is only done on this 2 points here. So we are not sealing against 300 or 400 bar anywhere else, which means you need to have a ferrule perfectly having the same shape as the inner, like the inner shape of your port. Therefore, the ferrule has this specific shape with the correct angle. And although the Vichy ones and the Shimatsu ones look very much the same by the naked eye, it's not exactly the same angle. It's a few degrees not the same, which means you could use it for sealing, but you have then, as I said, we are sealing only at these 2 points. You have a little bit more of that word's changing. When we have now liquid entering here, it's normal that a little bit of liquid flows back in this area here. You cannot prevent that, but it should not flow behind these sealing points. But when you now start to use wrong ferrules, this area gets bigger. Then you have higher void volumes on the connections. Okay? You are not destroying anything, at least as long as you do not apply too much force, but it won't be the perfect connection that is intended. Okay? Okay. Therefore, when you look on the instrument, you will see that when we set it up, that we use different ferrules and also different nuts on all the Shimatsu parts compared to the valves on the PAL. That's also important when a customer wants to change a connection. Typically, I know from my experience, when a customer has, let's say, a shelf full of parts, they are just using that might look fine, but it could be the completely wrong part. We also have 360 micrometer tubings, which is basically fused silica. These have so-called peak sleeves. Peak sleeve is in fact just a P capillary. We will see that on the instrument, I think also on the next slide, that is squeezed together in combination with the same ferrules and the same nuts to have a sealing also for a fused silica capillary. But I think that will be in one of the next slides. Ignore this part here. As we have already learned, I hope everybody can see this chromatogram here. Otherwise, you need to look on the slides in the PDF or in the Teams chat. As I have talked about that last week quite a few times, we had the problems on the dichloromethane pump that quite quickly Parylene got from the black peak shape very fast into the pink one. This is because we had this unwanted reaction on the HPLC column where the following happened. You have the pump, that P. I ignore the, let's say, we have a second pump, we are connecting it together. We have somehow our injection. And then we have our HPLC column. Okay, I think that's quite easy until that point. We have a pump with the DCM, which unfortunately interacted with the stainless steel surface on the pump, releasing basically Fe2 plus and also 3 plus ions. Not important which one it is. These ones could be carried and to the top of our HPLC column. So then we have our iron ions on top of our HPLC column. As you can imagine, in the column there is silica, which has around of a surface area of around I think 700 square meters per gram. So this is quite big surface inside the column. We are now somewhere spreading our metal ions, and what we now have created is a very nice catalyst. As you know, catalysts are typically inert materials like silica in this case. We are somehow spreading our ions on top of the surface. And now, unfortunately, you can create from, when we take our aromatic compounds, we can unfortunately transform them now into something like that. Yeah, so we are putting a chlorine from the dichloromethane onto our aromatic compounds. This basically now is not any longer MOA. We have just changed that on the HPLC column. And that's basically what you are seeing here. In fact, the peak is not only start to tail, but you will have, this is a composition of now multiple compounds. So it's basically Parylene, which partially is formed into chlorinated Parylene, but you also have, with very much the same retention time, also chlorinated versions of Parylene. It's not only one chloropyrrolene, but when you look onto the chromatograms in GCMS, if you like, I can show you later. you will see that you have different isomers with different chlorination states. In the end, it was quite complicated to find out the source for that, as you can imagine. But what we did is, till that point, that we installed an EDTA trap column. So it's basically just an empty tubing, the same one we are also using for aluminum oxide, completely filled with EDTA. I am pretty sure that you never have to replace it because we are not talking about many ions we need to trap. So it's filled, it's installed, and it's only needed on the dichloromethane channel. Therefore, we have this additional column inside our binary pump. Any questions regarding this topic? It all comes down to dichloromethane and the stainless steel surfaces. There seemed to be some interaction which is quite normal, and the easiest solution for that was just the installation of such a trap column.
So the black chromatogram is with EDTA trap.
Yeah, well, let's say before. I think this is from the time where we investigated. So the black trace is with a new HPLC column, and after injection, a few times of internal standard. So no samples. This peak shade deteriorated into this peak shade. Unfortunately, as soon as it looks like that, there's no easy way to regenerate the HPLC column because ions is very difficult to remove. As I just said, it's very high surface area. There's very much interaction between ions and bare silica. So it's very complicated to get that out again. So unfortunately, it means the column most likely needs to be used for some other application, but not anymore for aromatic hydrocarbons.
This is not happening in a Zealand pump.
Normally not. It's funny that we have seen it, let's say, on one or two instruments, but these were already quite old. So on new instruments, we typically do not see it. I don't know if the quality of the stainless steel is another one. I don't know what type they are using. And it also is important what type of passivation procedure you are using. Normally, when you are creating the pump head, you are building everything together. It's not directly shipped to a customer. There is quite complex passivation procedure where you would use something like citric acid or I don't know what's the correct term, nitric acid. So HNO3, which is also a very strong passivation solvent for stainless steel surfaces. But it comes down to how long and quality of the stainless steel and all that kind of stuff. And to be honest, we never tried again to remove the column because it was, as you can imagine, the time you are losing just by checking if it is necessary or not on each instrument is much longer than just installing the column every time.
How long?
Never,
Yeah.
never.
Like 5 years, 10 years.
Because I think at a certain state you have some kind of, let's say, equilibrium that the pump head might be completely free of, let's say, ion leaching as soon as there's no active surface anymore. And normally stainless steel, I think the stainless steel used is, I suppose it should be 316, which is the number you need or you are using for stainless steel, compatible also with chlorinated solvents. And I suppose at some stage there should not be any ions leaving anymore. Yes, until this was what we talked about last week. When you are turning off an instrument for a longer period of time with dichloromethane inside of it, it will convert to HCl, and then it's basically the very low pH value because this type of stainless steel is, I think, can be used till pH 1.5 or pH 2. But when you are lower than this, it will also start to corrode surfaces. And of course, it was also one idea, you could also use the so-called bio-inert pumps, but these are even more expensive. I would not use IPA because as I said, IPA, when you are not careful, you have a trace of IPA on your silica HPLC column.
Okay.
And then of course you need quite some time to get it completely out. So it's faster and easier. Take a beaker with hexane or a small bottle. Take the tubing of your dichloromethane and put it in there, and just flush everything with hexane. I would not recommend, because it's easier and safer when you use hexane for it.
And so makes your B line beautiful.
Yeah. In fact, it is much more dangerous to put the line of A into B than putting other way. A B into A is very dangerous, but putting A into B, so traces of hexane in the dichloromethane is not that of a big issue. Because when you have, let's say, 0.001% hexane in your DCM, I'm pretty sure you do not see that. But the other way could mean that you already have too high detention or too low of a detention, so too much DCM at the beginning of the product. When it comes to the configuration for the GC, very, very basic. As we have learned, we do not use any PTVs or any split-splitless injectors or any MMI. It's just basically when we buy it without any inlets. We're using 2 FIDs, and the only thing we are changing, we are using high temperature FID jets. Basically means this the 0.8 millimeter hole inside, because it has less clogging. You can imagine, we have seen chromatograms where you have at the end of the chromatogram still much and more eluting, which means very high temperatures. And these compounds sometimes cannot even be burned inside the FID. So over the time, you will see deposits of high boiling compounds on the top of your FID jet. And with the bigger opening, it's less of a maintenance interval. We do not see any other problems by that, so no decreased sensitivity or something like that. It's just to prevent clogging, because with the original FID jets, it basically depends on the matrix the customers are analyzing, but we have seen cases where we needed to clean the FID jets, let's say once a month, because of the very high boiling natures of compounds depositing on top of the FID. It's not happening this fast when you are using bigger openings or yeah. Instead of using an inlet, we have learned that we use our Connect LCGC box with the carrier gas supply, and it's basically only the part you are seeing here. It's a T-piece, very simple, just a T-connector connecting the carrier gas, and this blue line is a 360 micrometer capillary connected to the PAL on top. So this is the T-piece I was talking about, where we mix carrier gas and liquid. And then when you look on the GC, you see fancy stuff like that. You typically do not know. These are our solvent vapor exits. So our valves that can open and close to divert the gas flow either into the waste. You might see that we have here PTFE tubings. These PTFE tubings are basically going down to a solvent bottle where we collect all of our liquid waste coming out of the GC. We will talk about these capillaries in a minute. And important, two solvent vapor exits, because of course we need one for MOSH, one for MOA, and they all are heated. They are heated to prevent condensation inside the valve. That's the only idea behind that. Because as we have learned, our solvent is evaporated in the retention gap and it's leaving the system in a gaseous state. It only is allowed to recondense in the tubings here. So everything until this point here should be in the gas state. Basically, it's basically the idea behind that. We want to prevent recondensation inside the valve because it could potentially disturb the closing and the opening mechanism. As you can imagine, a solenoid valve is basically also some kind of a piston moving up and down, and when there is liquid in between, it's harder to close when it is only gas. Therefore, we are using heated solvent vapor exits. And just for you to know, for instance, Börstel is claiming they can use it without heated solvent vapor exits, but I know from customers that it doesn't work without heating. So customers from the United States having Börstel instruments retrofitted a heater on the valves because it works much better and much more reliable when you have heated solvent vapor exits. The box itself takes care for the carrier gas supply. It controls all the heating of the valve and also the timing of the valves. That is basically what is done by the box. You might ask why we decided for the box or why we have done it in this way. That's not so important for you, but it allows us to use every type of a GC without major changes on the hardware. Because as you can imagine, every important part we need for the evaporation stuff is controlled by our own hardware. Therefore, it's easy to switch from, let's say, Shimadzu to Thermo, Agilent, Varian, Bruker, or whatever. That was when we designed that in 2014, the basic idea. Now let's have a look on the capillaries. That's now an Agilent picture, but it's exactly the same. We have these capillaries here. Each solvent vapor exit has its own, and it's basically just 1 meter of a very narrow pure silica capillary. It's untreated pure silica, so quite cheap, and it's basically only there to prevent back diffusion after the solvent vapor exit is closed. Which means, up to now, I just made it easier for you, but we need to keep in mind that we have our TPs in the beginning, we have HPLC, we have carrier gas, we have our retention gap, SVE, separation column, FID. Okay? When the transfer is finished, so we have on Friday found out the timing when to close our solvent vapor exit. We have liquid because it is needed, or solvent front inside of our retention gap. As we have learned, this is needed to retain our volatile compounds. It also means when this bed is closed that we still have a gas vapor full of our solvent also inside the valve. Let's say up to here. When we now close the valve, so it's closed, and we would heat up our GC. Unfortunately, it means all of the gases hexane would be diffusing back into this way. Okay, that's unfortunately one of the biggest issues why we cannot just open and close, because we need to close at a time where it's still liquid inside, or let's say solvent that is evaporated. Therefore, this is not a completely closed valve anymore, but what we are using is these capillaries, which are giving a very high restriction, meaning there's a very low gas flow of carrier gas exiting also these capillaries.
So it's not completely.
It's not completely closed to prevent this situation. In fact, it's not looking like that, so it's not open and close. But we have our restriction capillary here, and then our solvent vapor is exiting this way. But it also means there's always carrier gas coming out. Okay?
Very low amount.
A very low amount compared to the stuff that is running through the separation column. It's a very low amount. You can imagine it's 1 meter times 0.05. Typically, the GC column has 0.25, so 5 times more. But remember, the radius of a column goes into the equation power of 4. So it's not 5, but 125 times 5. So quite a lot of pressure difference or flow difference here. But it also means for you in, I think, one week, one of the issues that when these capillaries get clogged, you will have the situation I just painted there. So all the solvent being stuck in the instrument, not giving you a very nice solvent peak that we have seen up to now, but it starts to look very ugly, or it's not only 2.5 minutes broad, but 10 minutes. But it's all related to the capillaries we are using there, or maybe they are just clogged. I will be back in a second.
The ID.
Yeah.
Is affected in the formula, right? That's all probably. That like how often. So like if you calculate the ID of that join versus the ID of the capillary. The capillary in the because it's capillary in the analytical column.
0.25, 0.05.
Yes. And then it's not only 4 times, but it is
5 times.
it's not only 5 times, but it's 5 to the power. That one is in the formula.
Oh.
It is like gas system is. Gas.
Now, just from catching the few words, you need to look into the formula to calculate constant flow on a GC, and there the radius has a very high. I think it's to the power of 4. Therefore, radius of a column is much more important than a few centimeter, more or less of a column. This is what you're seeing on the picture.
It's just a heater block, right?
This is just a heater block. And just to let you know, this was the version we are using before. So we had in the past other valves than we are using right now. I don't know if you have that old instruments already sold. I think during COVID, we had a problem that the supplier of the left valve stopped the production of it. So we need to replace to another type of a valve. Is any of the instruments you have sold during still from that time? So you might notice that the valves are now looking different than the one you are using.
Changeable.
Hmm?
So if we replace it with
Of course,
again.
of course.
Change in pair or can change one by one?
One by one. It just looks funny because we have one of this and one of that, but it's perfectly fine. When you compare the valves, and we can open them, but the older version is a real 3-port 2-position solenoid. Which means the older version is exactly what you're seeing here. It switches this connection here either to that side or to this side. Yeah. Unfortunately, on the market, there are not so many solenoids that have the specifications you need. Therefore, the new valve, in fact, is not a 3-port solenoid anymore. It's a 2-port solenoid that is designed in this way. In fact, it is not open and close, but we have a T connector connected to an open and close valve, which means when we are opening the valve, the capillary is still connected to the flow. But as these are very thick tubings, everything is basically going out into the waste. And when we close that capillary, this valve, basically all the flow only can exit through the capillary here. Therefore, it's basically not the same type of a valve we are using anymore. But it was not possible to stay on the same type of a valve because from the specification point of view, there are not so many this small valves that have all the specifications needed. Because this is now the specifications, for instance, for the newer one. So of course they need to be pressure stable up to the pressure we need, which on the carrier gas side basically needs to be the complete range a typical GC needs. Not only much more, but you know that the typical high limit for gas pressure in GC is 10 bars. This is typically more or less every vendor has as a maximum specification. Not so important for much more, but when you are doing fast GC on 0.11 millimeter columns, you've got to very high pressures. And it needs to be coated inside with some special materials that need to be compatible with dichloromethane. Because when you just take cheap valves, they will deteriorate from the inside because the dichloromethane vapor will destroy the valve from the inside. Therefore, you need to use some special kind of valves, and basically it also needs to withstand the temperature we are using for the heating of the valve. Therefore, it took me quite some time to find a replacement for that. And we were quite lucky that the new type of valves were available. Therefore, believe me, it was not that easy. Yeah, that's what I've basically put in here. Older valves were 3-port 2-way valves from Parker, but they are not available anymore. But you can still have instruments that have also old type, but they can be replaced just by unscrewing the 4 connections, put the new valve on top, and the connector, etc., is all the same. What's not installed on the new valve, of course, is there's now no T connector installed. You see there is a blank hole.
Yeah.
There would be installed this T connector with a short capillary of a tubing. So this part here, to have it completely in the same state as the old one.
So for the old one, that one is from up in the top. The other from GCL is
GC often would be, honestly, no idea, because it's looking the same. Would be found out when you are putting gas on the one side of the district. Will be on the front.
How about the waste? Waste.
On the top. Waste on the top and capillary on the front. I just did not put the picture in there because we sold it the last time, I think 5 years ago.
So this cartoon representation is the new block.
Yeah. And when we just want to have it a little bit bigger, that would be the complete valve. So with the T piece in here. We should see that later on the instrument. We are using just basically a stainless steel capillary to connect these 2 sides. Yeah, so you have seen that when you did not use them up to now, that there is unscrewable connectors and there are ferrules inside. It's important, it's a 2-part ferrule. It has a front part and a back part. So other than the ones you are used from the HPLC, Svetchlock is using 2-part ferrules, a front and a back ferrule, and you need both parts for sealing. You cannot just use 1 part for the sealing. So therefore, it's basically just the valve connected with a short capillary. I just put for you the correct length here inside. So it's 2.7 centimeters. So in case you need to do it or need to connect it by yourself, 2.7 centimeters is exactly the length you need to get from this point to here so that you have enough space for the T connector. But normally when you get it from us, it should be pre-assembled. Then on top, you are connecting your Fusilica capillary. On the bottom, we will see that this is the exit of our T connector from the GC. And on the end, it's just a cheap PTFE tubing put on a little bit left of a stainless steel capillary. I think this can be seen on this side here. See, this is the exit of the valve on the back side. We are just typically using a few centimeters of stainless steel capillary. Can be from the HPLC or can be from the T tubing. and then you are just putting that on top of you are putting the PTFE tubing on top of that, so that all the liquid that recondenses in the PTFE tubing can be diverted into your waste collector.
So at the waste pot in the box, we connect the stainless steel first, and then PTFE.
On the back side, yeah. You're just taking a few centimeters of stainless steel, so that you have enough length. But we can see that on the instrument that you have enough length to put on your PTFE over it.
This is pre-assembly right now.
This part here, of course, we cannot pre-assemble all PTFE stuff, because this is basically also there on any instrument. You can just reuse this part.
Just curious, at this stage, normally the things burn out are already vapor, etc. So then you connect to the waste, right? Is there anything really collected at the waste bottle in general? From the waste, right?
Yeah.
I understand it attached to a bottle, but
it is going down into the HPLC into the HPLC waste.
Oh.
Yeah, because it's basically just recondensed pure hexane or pure dichloromethane, probably much purer than the one you have started with. But you are just collecting it together with your HPLC mobile phase waste. We have scud filters on the HPLC waste, meaning there's an active carbon filter in it, so that you also do not have all the stuff in your lab air. So I will just show it in here, but I think it makes sense to have it later seen in the instrument. That's basically the inside of our GC. We have from the top our two detention gaps that are connected on top with our T pieces. The front one and the back one. These here on front are our two detention gaps. Both of them are connected to one of these T connectors, and each T connector has its own separation column. So on the back, we have two separation columns, each connected to the FIDs. You see, I think I made this picture on my instrument. I'm still using the normal graphite nuts, but typically we are installing everything now with the ClickTech. I'm just confusing the names. ClickTech connectors. These T connectors have the tubing onto them, and we are typically installing it in a way that we go to the right side of the GC often, then to the top, then back, and then we are going back to the top out of the GC, because here are our solvent vapor exits. So basically the capillaries that are here will be connected here. So that all of our evaporated solvent evaporation is done at 60 degrees. So it's all vapors. It needs to be in the same gas state also inside the T and the valve, and it's not important anymore if it recondenses in the PTFE tubing. Therefore, you will see doing evaporation always liquid drops inside the PTFE tubing. You can imagine, just as another example for customer mistakes, when this tubing here in your waste bottle, we have sometimes customers doing that you have a waste bottle with a screw cap on top, that you have your PTFE tubings. Then you have a customer getting into a state where the end of the tubing is stuck between the cap and the thread of the cap, so that effectively the end of the tubing is just blocked. Of course, you can imagine a blocked exit here is not giving high pressure because all these connections, especially this connection here, is not tight, but the liquid cannot be transported anymore. So this will also give you another looking GC chromatogram, basically with all the solvents still inside.
And temperature. The temperature.
Temperature is set on temperature basically just needs to be higher than the boiling point of the solvent. For the older valves, not sure why, but we got up to 120 degrees. When we introduced the newer ones, I decreased it to 80. But if it is 80 or 120, completely not important. So therefore means when you are replacing a new valve on an older instrument and it is set to 120 degrees, it's fine. It's just needed that it's higher than the evaporation temperature, let's say boiling point of the solvent.
What make you guys change from the normal graphite fluid to ClickTech?
For ClickTech, honestly, it was only the non-linearity of the instrument. Because ClickTech has the advantage, as you know, when the ferrule is stuck on the column, it will be always at this exact position. At graphite, normally people are used when they are installing columns. They are going to the end of your FID jet and they are retracting a bit. I know this is not the way as you do it typically on Shimatsu equipment, but many other vendors, when you are installing FID into an FID, you just put to the end, then you are retracting a bit, and then you are fine. Unfortunately, it does not work the way on Shimatsu equipment. Therefore, you know that you have this installation tool with the correct length. Of course, the disadvantage with graphite is that you can still move the ferrule on the column. Therefore, it was too complicated for the people to be exactly at this position. Therefore, ClickTech was easier. Of course, also more expensive. You know that you could also use a septum or something to fix it here. I'm doing it in my instrument the same way, but it was too complicated for the customers. Therefore, nowadays we are using ClickTech for that. Yeah, everything stainless steel. FID not that important, so could be graphite. And it's basically just that we need to go out at least up to 370 degrees. We have customers, at least in Germany, that go even up to 400 degrees, which is perfectly fine. It's all stainless steel, and I think the Restec columns are specified till at least 410 degrees. The retention gaps are installed in the front of the GC, while the separation columns are in the back. It's because from maintenance point of view, these need to be replaced more often than the separation columns. Therefore, it's easier to get them into the front. But in the end, it wouldn't be important, but that's how we set it up normally. As you know, at least up to the 2030, FID is not grounded. Therefore, we need to use an isolator. We're using the fused silica capillaries or shields for that. But coming to the T connector, because that's what most people do not know. I was talking already a little bit of that, but it looks basically like that. So it's so-called sil-type mini union. So the one you might know when you just want to connect two columns. Nowadays, since a few years, Trajan also has the so-called micro union, where you have one ferrule for two columns. This is still the version where you have two ferrules to connect two columns. We have soldered a stainless steel capillary to the side. And as I said before, it's then basically installed in this way. Why I decided to do it in this way is the stainless steel first of all, can be pre-bent. So this is one of our templates we have designed. And I would advise that you do yourself this as well. If you like, I can get you the dimensions, but basically it just means you're taking some stainless steel capillary and you are bending it exactly the shape you need, because then you can pre-shape everything outside of the instrument, put it inside, go through the open sealing, and then you are done. Because trying to bend everything inside the instrument looks really ugly. So basically, we are doing installation, or before that, we just made ourselves those templates. Then you can pre-bend everything. Unfortunately, we did not manage to solve them pre-bend. That would be unfortunately too complicated, and I don't know if in Australia would be somebody who has time for all the bending stuff. Therefore, when you buy them, they look like this. So this is one of these capillaries who have 1 meter of tubing soldered to the connector, and you need to get it into the shape you need it. Because unfortunately, of course, depending on the GC vendor, it's not the same shape.
So the template we need to prepare ourselves.
You can either do it by yourself, or if you like, I can send you pictures and the dimensions. Then you can just copy it. You can do it the same way. When you need to replace one, you are just unconnecting, getting it out of the system, and you are just bending the same way. But I can, if you like, I can also send you the dimensions of the template we are using. Only, so there are effectively two scenarios, or let's say 3 scenarios.
Inside it. There is no pedal inside it.
That's true, because I was afraid that you are losing them.
So actually, it should have pedal, right? It should come with a pedal, right? You purposely remove, right?
You will have pipe with them, but honestly, normally a customer should have a few boxes of them, because you need quite a few of them, of the pedals. When it comes to when to change them, just that. So basically, what we have seen as customers, because of course this is, let's say, some connection that could be, since this tubing is just connected in here. When customers do not know that they, of course, these are quite small tools they are needed. Especially when you have HPLC customers or customers that do not know about gas chromatography. They are not used to work on these small tools. And again, when they just hold it this way, when you are not used, of course you need to have one spanner to fix that, and the second one to unscrew. When you now use these ones, let's say in this way, and you are flipping out of here, there's a high chance that you will break this connection here. Then it is leaking, and you need to replace the whole assembly. The second one, what I said before, this is exactly the same connector pack here. So you can prepare everything outside the instrument. See that later on the slide. But since people are typically used to use ferrules with the cone facing to this part, and not with the cone facing to that part here. I think it's easier when I show you the next slide. That people are destroying this part because they are not used to that it should look this way. because normally every other connection on the market will have the cone facing into this direction here. Therefore, when you press the cone inside, you will destroy also this connection. And then you also have to replace it. A third scenario would be, of course, also that could be one thing, but when you have cloggage inside here, which typically only happens when people did very bad sample preparation. PET or non-saponificated stuff is clogging this part here, then might be necessary to replace the assembly. But honestly, you could also get it out from the instrument and just clean it and put it back inside. When it's just stuff inside, especially when you have an HPLC pump with 700 bars, you will get it out again. So therefore, I would say the most common scenario where this needs to be replaced is that people are not aware that they need to fix the part when they are changing stuff. If you hold it once again for me, you will do, all of you will do this later on the instrument. So you will see how this will look like. But opening and closing should not be done just in this way. Typically, what I recommend is use your fingers as a support. When you have your finger at least on the top, you cannot have any problems in this way. When you fix it in this way, it is easier. Another way, but this is dependent upon how you want to work with that. So this is now a little bit of a commercial for a German company called Cleanpex. It's coming from town next to mine. This is not the same like a spanner you would typically use to change your tubing at your sanitaries. This is basically exactly the same shape as you can have on a normal spanner, and when you adjust it to the correct height, and when you grip here, it will be absolutely stable. Yeah, but this in the end depends on your personal way of how to work on the instrument. I honestly found that more complicated than using tool. So in this way, and use your fingers. But especially when you have very big hands, so as you know, I have very small ones, it is easier just to use this spanner, fix this part here, because then you can work without any problems on these connections. Otherwise, it's always advisable when you do it in this way that you need your finger to support that.
So you need to buy these markers.
These you should have both. Each instrument has both. One of the normal ones and one that you see also there on the slide, because you can prepare all connections outside of the instrument. Yeah, guys want to see it? We have a lot of different
I brought some traditional cakes with it's like in our Asian countries, it's like a traditional way that you can have it.
What type of?
It's just some dough outside like mochi, and then inside is Okay.
You? Do you eat it with or just out? I just want to ask.
Yeah. Do you don't need the, yeah, I know some. You can just just throw away the leaf. Thank you.
Yeah, don't eat the leaf.
Okay, I understand.
Yeah, because I saw my friends, we just give you we have another history which is like white color called bun. Chinese version. We give you the paper always for sure. Have you tried some of the things that
I really like the small ones. That's effectively this temperature here. So the oven is set to 60 degrees. Our temperature sensor measures 61, which is perfectly fine. But this is the temperature probe needed for the constant flow calculation. So unfortunately, constant flow always means you need to have an additional temperature probe inside the GC oven. The ones of you who know the Optic 4 from GL Science, it also has a temperature probe that needs to be installed in the GC oven. Because for constant flow, you need to have this number for the calculation from pressure to flow. But now coming back to the connections.
Is the temperature probe spoiled easily?
No.
Did they experience it?
I never had
Able to
never. 2 times.
even I say the during installation and after around
So
1 month.
you see that, I don't know if you can see that, but the tip of this line here looks a little bit different than this part here. The temperature measurement is done only at the tip here. Basically means in this part here, I could do it like that without any defective. So no idea how you managed to get this part destroyed.
Because installation during installation, Mr. Two found order new one from you. And after around 1 or 2 months, the new chain again.
Somehow this temperature just reflect like 0 or 30 degrees, something like that. Whenever they set, this one will not go up. Always display 200. This one display 100 when it's hot.
It's a green.
Get the number, but it's not exactly.
Oh, very high. It's a 300. It's a monitor.
Yeah.
And it's a second.
No, it's a PT. For the ones who are not aware how temperature measurement works inside the GC. A PT100 means platinum filament and so PT abbreviation for platinum, and 100 means 100 ohms resistance at 0 degree. So 0 degree Celsius. When you would use a conductive meter, or is it a resistance meter? I think it's that. 0 degrees Celsius on a PT100 means 100 ohm. When you now heat up, let's say to 370 degrees, it's much bigger than 100 ohm. Because you have a direct relationship between the electrical resistance and what would be the consequence when you would just disconnect the PT100 in terms of electric resistance? Oh, infinite resistance, which means infinite resistance is converted to normally, depends a little bit on the instrument, let's say 600 degrees, which is not shown anymore, but the instrument the instrument knows by that it has a disconnected PT100. Therefore, you get also a message from, let's say, from the Shimatsu FID or whatever, when a PT100 is disconnected or destroyed, which means that the platinum thing is somehow broken. You will get a message from the instrument because it measures effectively infinite resistance. That's how you translate electrical resistance into temperature, because there is a calibration plot between temperature and electrical resistance. This plot is saved in the software of the instrument, and it calculates temperature against resistance. And this works, I would say, this is the way on 99% of all temperature probes. I just need to interrupt here because we have also something called a thermocouple. This is a completely different type of temperature probe, but typically all lazy, or let's say slow temperature probes that do not need to be very fast work in this way. This is the case for all Shimatsu temperature zones, and it's the same also for ours. It's exactly the same. Just now a question for you. CTC, for instance, uses PT1000. Any idea what this could mean? It's then 1000 ohms at 0 degree.
That's PT200 also.
Only. Unfortunately not, no. It is basically just PT100 and PT1000. That's the two types that are used on the market. But I would say basically, let's say 90% of all important stuff is always PT100.
So is it PT1000 more accurate?
Not, yeah, I suppose it could, but it could also be related on how accurate your electronics is to get out the value of the systems. As you can imagine, measuring to several digits can be more challenging than just 1000 value. I suppose it's basically that, but I'm not 100% sure of this.
Okay. In their case, they saw the probing damage. As
Yeah, when you are seeing temperatures like our hardware, the highest temperature you can see is 356 degrees. When you are seeing 356 degrees, it means you basically have disconnected your PT100.
So it's the end there that you have to be careful.
Mm-hmm. Yeah. It's basically this part here is not this important. You could also bend a 90 degrees angle inside, but it's just the tip. What we have also seen is the end of that probe, of course, has something that looks a little bit like that, because it ends in a connector that's then connected to our box. And these are on that part very thin connectors. So you need to be a little bit careful that you do not stress them too much, because these are very thin lines on the PT100. But honestly, no idea how you can manage to get two probes damaged in such a short period of time. No, even I have no idea. If this can, we definitely need to trace it back because it's not normal. In the meantime, do you already have feedback from your customer regarding the high sodium sulfate in the vial?
Different.
Yeah, it's different. It's different systems. Okay, but but the question is still the same. Do you already have a positive feedback from your customer for the sodium sulfate? Because this was the okay. Coming to handling stainless steel columns, did all of you already know from the past how to work on stainless steel? Let's say fused silica type of capillaries. Everybody is aware how to cut them and all that kind of stuff. So it's nothing you need to learn or you need to see.
We can see you.
And how much do you pay for this? How do you judge? Yeah, using the external.
You mean on here or
Yes,
which one?
yes.
So I think I put very nice pink indicators on that slide. I think it's quite understandable how long you need to install. But first of all, regarding stainless steel capillaries. So this is now a used retention gap, so I can do on that whatever I like. I send it in here in advance. And now one of the biggest disadvantages of stainless steel compared to Q-silica, you know, when you take Q-silica and you do like that, it will just break. Fortunately, here you can even do something like that. Depending on how much you are squeezing it, you're of course changing the inner diameter, which is what I meant about also squeezing in this area here. Of course, when you have a tight bending in here, also this means that the flow is of course not the same anymore. When it comes to the cutting, I have seen people holding it there and trying to do this one here, okay? You can do it, but you will not get a clean cut. In fact, what you should do, take your finger, take your cutter. Fortunately, these cutters, not both sides are the same. One typically is smooth, the other not. So what I typically do, I try first on my skin to see which one is this smooth one and which one not. I take this smooth one, and then you basically on your finger just need to do 3 times, and then you are doing this. Then you are done. That's it. Smooth one.
Oh, metal one breaks so easy.
Yeah.
Yeah, I don't
Yeah, of course. Yeah. So the idea is basically, again, do not try to squeeze it, and don't. I have seen people really trying like that. Okay, but it's basically you just take it on your finger or a little bit in front of your fingers. You just basically need 3 or 4 cuts, and then you are doing like that. Then you get always a perfect cut. And even if that now sounds a little bit easy, believe me, I have seen the craziest cuttings and the craziest endings and bendings and all kind of stuff on these capillaries. It's exactly the same also on the separation cutting. Of course, much thinner, but basically exactly the same. You see, this one even has its click tag pedal still connected. It's also an old one.
You need more force than normal glass cap.
Yeah. You of course you need to stretch the capillary. And you see also here one disadvantage of stainless steel. I don't know if you can see it, that it is not straight. This one here. And which of course, again, installing such type of a capillary, even when you are interacting it, because you can have something like that, even when you have it now not installed to the end of your FID jet. Even this, of course, is doing some electric connection. Therefore, to be on the safe side, we always use the sleeve. And we, of course, use always the installation length tool from Shimatsu. You know this, I think this is, I don't know how it's called, but the exactly hexagon one, where you can measure the correct length for the click tag ones, and you can, I think with this special nut, pre-tied it. Should be always done in this way.
Just for your diagram, right? Because the I see from here the separating column and the retention gap are inserted
Yeah.
into each other.
Yeah.
So how we know how deep to go? That's why I asked.
How deep? Effectively, you are seeing that
So
on this picture here. You see that this is the exit of your retention gap.
yes,
The exit of your separation column, and this is the length of your retention gap. When you are installing it, this one corresponds to that one here, and this one is effectively this length. Means the retention gap is penetrating the connector more or less to the middle, and the separation column is penetrating once through the complete connector. In the end, it is only important the separation column needs to penetrate into the retention gap. When they would just be floating, all of your sample would be just lost, or let's say diffused inside the connector. But when you are putting one into the other, the sample is directly transferred to the stationary phase of the separation column.
so the important thing is the separation column just go all the way up,
Yeah.
and we just feed in the retention gap.
We will do that. We will do that in a second. But effectively, since you have these tools available, so this is exactly what you are seeing here. You can prepare everything outside the instrument. Also want the 0.32 millimeter ferrules and these ones. Can you get in some of them?
Yes,
Ah.
Wondering whether our better confidence actually we often
Good to know.
because they are analyzing so they want to be there.
Good to know. Now this one, this is one, you should have not that one, not that one, also not that one. Then the one more is I'm pretty sure that you would have Then you are doing a finger size. Then now you can see that you can move the capillary. It's not important if it looks like that or if it looks like that. We are cutting it either way afterwards. Then you need to have a little bit of experience that this now is already straight enough.
Don't overtime. Not overtime.
You can.
Yeah.
You can. And we will do this in a second. So then you are basically untightening that. You can see now it was too little force. So I would need to do that basically once again.
You want the problem with
Yeah. Let's do that once again. Sometimes depends a little bit the nominal diameter of the column, of course, and the nominal diameter of the parallel. Sometimes have some variation, which means you need to be careful because sometimes you need a little bit more or a little bit less force. Let's see my entire bit now. Start or not? Yeah.
The one you mentioned, in fact, the solvent peak is over 10 here.
Yeah. Yeah. It's basically coming to that. So this is now tight. What you're now doing is you take your ceramic cutter. Yeah. You. No,
completely.
it's completely fixed now. So what
Feel
you,
the tension.
Hmm?
Yes, there's that feeling. Yes.
yeah, it's
If over 10 here will affect also, right?
yes. We will do this in a second. I just want to show you then what this picture basically tells you is you are holding that next to that and you are cutting more or less at the middle of this connector. That's what this picture is telling you. This length is basically going up to the middle of the connector. Does anybody of you have an idea why it is the middle? This is not by accident. It has some idea behind it. Maybe it gets easier.
Yeah. You. Okay.
Maybe it is easier when I show you when I show it to you on the real connector. Because at the middle of the connector, this tube is going, which means we want to be sure that our vapors are exiting as fast as possible, which means, honestly, it is not that important.
Shorter is fine.
Shorter is fine, longer is not so fine anymore. Especially, what would happen if I would just, where is my second spanner? Thank you. So we have now connected that, and let's pretend we would cut at the end of the connector. What would be installed on this side? Separation column, and the separation column has its own ferrule, which would then seal completely the exit of the retention gap. No evaporation anymore, also a very common customer mistake. Therefore, we have this picture in the middle. I think it is easy to remember. One column to the middle, the other column to the complete length. And so basically, you just hold it next to it, and then you are cutting, as you said, in the correct way. Shorter is fine, longer not. So you have basically now a connection to the middle of the connector. And that's it.
It's fine.
That's fine. Then this is fine and could be then installed in the GC. Now
You also can measure, right? And then
you can,
we can.
but when you have, okay, let's say when you have a ceramic cutter, this is fine. But honestly, you do not need to remember 5 millimeters or whatever. So, of course,
Yeah, that's what we do.
the separation column needs to penetrate easily into here. As you can see, I can put it inside.
So these need to be checked.
Yeah, this needs to be checked. That's the first thing. I will even explain what you should do because especially in the beginning, it's not so easy to feel how much force you need. What I will now do is I will keep it this way. Let's now apply more force to that. Okay. We have an idea what's now the problem of contact.
Let's go in.
Cannot go in.
Yes.
Because it's deformed.
So this now this is a bad example, right?
This was a very good now.
So let's see.
So this is wrong, right? This is wrong.
Yeah, but now you have one issue. Typically, look how long this column is and look how long this length is, which means the customer just installing everything. This column, which normally, when you do not know about the fact, would just penetrate more or less like here. So you do not feel it. So this is only actively felt when you put the column manually inside, or when you just prepare a piece of capillary to check after installing a new ferrule. Because in a working instrument, this capillary would not go beyond this ferrule. Yeah?
Yeah, actual scenario.
Does this make sense? And what we recommend by now, especially for the Shimatsu people, because there it is easier, you know that when you buy a new FID ferrule, the graphite ones, each ferrule has its own little stick. This stick has the perfect inner diameter to fit inside. You can put it inside during the fixation. Then you can tighten as much as you like, but you cannot squeeze because it has the perfect inner diameter for this capillary.
For the retention gap.
For the retention gap.
But
So-
must clean the graphite.
Hmm?
Must wipe off the graphite. Otherwise,
Yeah. True. But only in the beginning when you do not know how much force you need, or when you have customers that are not that flexible with their fingers. This little stick has the perfect diameter that you cannot squeeze this connection. Because when this is now in this state, of course, we have a blockage here, and you have potentially the same situation also on top of the GC, where you have such a connection a second time. So basically, either on top or here, in this way, it is having the same influence. You will only need to be sure that the ferrule sticks on the column, but not squeeze it. Because then you are directly influencing the flow rate. And there's not just a go, non-go situation. You have all kind of variants in between, depending on how much you have squeezed it.
so
But
as long
this
as,
is now, let's say, worst case.
so can I say that as long as I can fit everything nicely to the retention gap,
Not
deforming it.
not this capillary, unfortunately. This has an outer diameter of, let's say, 0.3 millimeters. This has a diameter of 0.53, which is still 0.23 millimeter, whatever, less. So it means only by putting this inside, you can not check if you have not squeezed it. But I would say when this fits fine and you do not feel any restriction, it should be fine to operate the instrument. But when you want to be on the safe side, I recommend use the stick from the FID ferrules.
Okay.
We'll take some sleeps.
Yeah, and I think after it's now time for lunch, or when do we
Take lunch.
after that,
To pull the graphite.
Yeah.
apply too much force so that you cannot penetrate anymore. And of course, it means you need to review the connection. Who wants to? So we'll just get you new ferrule.
Yeah, I think we got another set.
Yeah, then you can use your tools. I will just open the package. I don't know if it is. I never tried because I'm seeing everybody opening them this way,
Oh.
like that, because I'm always a little bit afraid to lose the ferrules inside. What I typically do is I just open it on the back side like that, because then you cannot lose anything else.
Yes.
Because they are quite small, of course, and the black one is.
Cut first.
Yeah, cut first. Just quickly see before. Yeah, it's fine. Maybe I didn't tell that. I get that. You can do this step quite slowly, of course, but you should do this bending quite fast, because otherwise there's a high chance that you are bending the material. So don't do that, because it might look like that afterwards. Or even when you manage to disconnect, it might be that you have a bending already in the tubing. So therefore, do this step a few times, but try to be fast on this one. But even this is perfectly fine, because now we have learned. I think we already had the pin.
Yeah, you want a pin?
Yes, because now we can do it already the correct way.
So the pin you are using the 0.5.
Yeah.
0.5.
Yeah, you can put this inside.
Oh.
And now when you are fixing it, you cannot squeeze it anymore. Of course, you have one problem by doing that. I will now only to show it. Where's the nut? Oh, this is the arrow.
The screw.
The screw, the nut. Ah, sorry. Sorry. Of course, when we now also put this inside first, of course. No, it's still here. I just want to show you that, of course, you cannot now anymore do this way, because when you would now fix it, it's nice that you have a pin here, but it does not prevent of over tightening here. So of course, when you are using this trick with a pin, what you can do is you do not need to cut afterwards. You can also install it directly at the correct length, so that you are installing it maybe here. Or what you can also do is you can just penetrate even more inside. Then you have, let's say, 1 centimeter that you can cut afterwards. So there are several ways. The idea is just that where this ferrule grips, that the pin is below that point, so that you cannot do over tightening. Yeah, just you normally do not need to do that every time in this way, because after a few installations, where are your tools? Yeah. Of course, you can also use 2 times the same one. Normally, on an instrument, you have one of these where this side is still free, but of course, you can also tightening, of course, with 2 of them, also fine. And one recommendation, of course, is that every service engineer should have one. Although every instrument has one. So we are not selling without these. So every instrument has one. But on customer side, sometimes they are losing stuff. And when you rely on that, you do not have your own, can be a challenge there. This is also a nice recommendation for customers. So when they are changing the colors by themselves and are not used to it, compared to you in future, as I'm pretty sure you will install quite a lot of them. You know how much force you need, so you do not need this trick with the pin anymore. But for a customer, when they are just changing a column, let's say every 3 months or whatever, with this you are always on the safe side. Yeah. I will just take it out one more time to get an idea how long it is. Because when you hold it next to it, you see that you need to push it quite some time in, so that you're on the safe side that this pin is still at this area. Otherwise, as I said before, you are tightening, but there's no pin below. Only to explain or to show you that in before, it's very hard when you have it in this way. It's very hard, right? This now is almost impossible to break. You can either, what you can do when you have no other possibility, you are taking a plier or something else, and then you can do normally the same. So I just did it now, not in the correct way, but not close. But it's always advisable that you have at least 1 centimeter so that you can break it by your naked hand. But sometimes, only to show you that when you are in such a situation, that even shorter periods or shorter lengths are possible, but you need to take a tool for that, and then it is exactly the same. Unfortunately, you cannot grip it by your fingers. So always advisable to leave as much space as possible, because it becomes easier to cut afterwards. Or you need to be absolutely confident that you are already at the correct installation depth.
But then the sleeve is quite short, then you also cannot leave too long
True.
outside.
True.
So now which route?
Yeah. Therefore, I'm still looking for this type of metal and also diameter so that I can supply longer versions of that, but I couldn't find it yet. That's me? So, yeah. Yeah. Yeah, the problem is now that you have it, that you are ended it at the end of that. And this is basically just now this distance, which means you need to cut it afterwards, definitely with the pliers. Yeah, so that's it is possible, but much more complicated than needed. So the pin is quite long compared to that. I will just take it out. You see that is even longer than the than this one. So there is more or less, even from the end, 1 centimeter on top. So just put it as much as you can inside, would be my recommendation.
Can we
Something that.
can we measure something like this? So the pin as an indicator.
Of course.
You should do out it.
You can do it also that way. Yeah, sure.
It should be a little bit.
Would there be a scenario you push the pin to the end?
Okay.
Yeah, you need to cut them. I suppose that with the ceramic cutter you cannot cut through the pin, but when you cut through the tubing, you can try to get it broken into parts again. But I didn't try it, so honestly, do not know.
Should be in the middle.
Yeah, try it.
I hope so.
We will see it. It's the training, yeah. So we are not expecting everything works at the first time. And as I said, the idea with the pin is just to be on the safe side. Even without the pin, when you have done it 1 or 2 times, you know, and you have seen how less force I have used. It was in some not even 90 degrees.
Yeah,
Okay.
Loosen.
It will be an extra retention gap to practice.
Okay, you got 2 sides.
No, I mean for customer, if we conduct patient training for them to
This one you will leave it to us, right?
You can leave, yeah.
or this
But this is typically what we are showing in the first. So when the instrument is installed and SAT is passed, we are showing all the stuff also to the customers.
Yeah, anything on. Or
Okay.
not quite enough. Wow,
Then you need to tight more.
Pause. It's okay.
Just on the right.
Because we cannot remove the pin. Yeah.
True.
I think
You will grip the pin also.
Yeah.
I'm expecting that it is this way right now. See? This essentially means already too much force. So when you would have done the same without the pin, you cannot get it. You would maybe be in the same situation as I was in the beginning.
The pin cannot pass through.
Yeah.
But at least
This is fine.
But this is
Yeah, sure. You just need to have something to get the pin out again.
But at least because of the filler, then the column is not squeezed in the squeeze. But then it's like a bit too long.
A little bit too long. I'm pretty sure that even this would be fine, but just to be on the safe side, try to stay up to the middle, not longer than that. But now it's basically impossible that you have over tightened, yeah, because you cannot over tighten
Because of the pin.
Exactly.
because the pin is
Yeah.
it's like
Too high.
0.3 something like that. Yeah, so you can with the pin basically you can just squeeze down to 0.5, not more. Does anybody else want to try in spring?
Yeah.
Just need to see what we can do. Have a second time.
ไม่ต้องผ่านให้ก่อน
because it yeah skip to the 你长波就不能那มี track
ที่ทำได้
其实就是摆
หรือไม่ก็ใช้วิธีแรกสุดขอยาวสิง่ายกว่า
Before tightening, just wait a second. I need to get something out of my tools, but I will be back in a second.
Alright, sacrifice this to try.
all one is actually I was being taught the wrong side how to use
这是现在
yeah 会了
Yes.
every try $5
Yeah, that is.
so eventually cost yeah more than the rest of the oh this
Yeah. You know what you do, man?
so yeah I'd rather we fail here than go customer side.
Can I have at least one of the column? Can I just get this one? To check something. So you need to be very careful. This one here looks the same. It is smaller.
This one I asked you before.
Yeah, this is when you do not order. This is when you do not order the correct one. Yeah, as you can see here, 1 inch of 32 of an inch.
So this
Not-
is correct one.
This is the correct one. When you use 0.53,
Each one.
that's not the correct one.
Potentially the for 1 inch.
Yeah.
Each for the radiation gap and M for the separation.
So
This one separation column.
Yes.
This one.
Yeah.
Flat to flat so.
32 with the two teach we you did spread yes sandpaper very big color
yeah, so unfortunately,
Okay, we listen.
unfortunately, the producers of such stuff, when they talk about 0.53 millimeter ferrule, it means it's not telling you anything about the outer diameter of a column.
Yes.
This is the inner diameter of a column.
Yes.
When the outer column, typically, when we talk about pure silica, 0.53 millimeter inner diameter always has 0.68 outer millimeter. ID and OD. Column outer diameter
Vocabulary.
for pure silica.
Yes.
Okay. Unfortunately, when we talk about stainless steel, the outer diameter is a little bit more. And we have now tolerances, not only on the column diameter, but also of the whole of the ferrule, which means you can have combinations where 0.53 millimeter ferrules perfectly fit on those detention gaps. You can, yeah, I can probably out of these, let's say 40 ferrules, maybe, let's say 8 or so, perfectly fine. But the other 32 are too small. But this is not a fault by the production of the ferrule. It's also not a it's not a fault by the column manufacturer. It's just the two tolerances, unfortunately, are going into the wrong direction. What we decided, therefore, I think now 3 or 4 years ago, is from going to, we initially started on this type of a ferrule. So therefore, sometimes you even still see them on customer side. We now use 132 inch, which is basically from the outer diameter around 7.6 or maybe more or less like that. So these ferrules here have an outer diameter of these ferrules have a hole of around 0.72 maybe, and these are a little bit bigger by definition. Therefore, these always fit on the retention gap, while these sometimes fit, sometimes not.
That one is the OD, right? 72 is the OD, right?
Whole of the OD.
Hole on the ferrule is. So there you cannot talk anymore about IDOD. It's just when you look on the ferrule, it's this diameter
For a metal.
for the siltite ferrule. So for these ones.
So this one no longer sell. This one no longer supply. You supply 132 now, right?
Sure. Therefore, it's always safe to use these. You still can use these, but you either need to check multiple of them, or what our customer support sometimes tell you, you can grind the column. When you look on the back side of my column cutter, you see that it is completely gray. The gray color comes from times where I was grinding the column. So when you make the column a little bit thinner, you can still fit those smaller ferrules on the column. But therefore, you have these two numbers. Yeah, you see from the colors. This color is coming from
The metal.
from the metal of the retention gaps. Does it make sense?
ไม่มีคำแทนหรอกกระดาษไป
To be honest, since I have so many of these also available at our facility, I try to use them first because I cannot use them for customer installations. This is only my personal amount that I'm using for my own instrument. So these are siltite 0.53, which is unfortunately a little bit hard to understand because the number is always about the inner diameter of a column, although the diameter in the ferrule corresponds to something of the outer diameter of a column. And of course, when I have 0.68 millimeter outer diameter, my hole needs to be a little bit bigger. Therefore, they are using 0.72. Unfortunately, 0.72 is too small for stainless steel because the wall of the capillary is a little bit thicker than for pure silica. Therefore, we are now using these, which unfortunately is given in inch, which looks more confusing, especially since unfortunately we have the same 32 now for both. 0.32 millimeters on the small column and 1/32 of an inch for the retention gap.
It looks the same.
I know it's confusing, but unfortunately that is also one issue of metric versus imperial numbers.
And should be in the middle for the head. Yeah, you can cut, yeah. You suggest to longer, yeah. It's just you don't use the sleeve lah. You don't use the filler. Then to make it just nice, using I only use 2 finger ropes. Then you put like that. Then just 2 finger. How much the 2 finger can do? That's it. If you also by that. I also do like this for 2 finger. If 2 finger then yes.
Depends a little bit on the force of your 2 fingers. So I could imagine that the finger force of you is much different compared to mine, or
or her.
My two
I know,
fingers just
I know. Yeah. Oh, but that's very nice. It looks very nice. And even when you are not installing with the pin, you can always check with the pin afterwards. What I also sometimes did is even when it is squeezed, sometimes when you force the pin inside, you can unsqueeze again. But only to some extent. Of course, when it's completely closed, no chance anymore.
Okay. Do we share the pin? Or is on it?
But I suppose we have a few of them.
Yes, we have a sacrifice.
This one cheap, nobody, we can open as much.
Yeah.
I think too big already.
Yeah, no, not the also.
Oh, it's 1.8.
Yeah. Or 0.8.
Oh, so
Yeah.
Therefore,
From 0.5. Yeah.
always
for
look
the
for
quite
an engineer
Yeah.
to have such a pin as a spare part available. Because you can check if everything is fine. Oh, wait.
Like you the
I just saw it away.
And don't be afraid. In the end, we did not talk about how much can you cut off the retention gap or not. When you are installing something, you can cut even half a meter without any problem in chromatography. Even 1 meter would be fine. As I've told you, that even 5 meters most likely would be fine. When you're installing them, you will see that you get from the top down to the other side of the connector. You will see the corner of the instrument, and sometimes you need to cut, let's say, 20 centimeters from inside to get to a nice installation angle. That's totally fine, but do not try to make any bending to get from one point to another, because that's most likely will introduce this friction in the retention gap.
So it's better to cut a little extra line rather than force it.
It needs to
You
be
You can.
you need to cut one.
I made experiments, as I said, you can cut 1 meter, still fine, but it will end slightly lower evaporation pressures. Because we have less restriction by the retention gap, so less material means you need less pressure for the same evaporation rate.
Then you just play with the figure up. And after you install it, you optimize. Yeah.
I'm more. It's basically the same for the separation column. So if you would like, or if we are already at that point, you are taking the 32 millimeters. I think it's one even here. The same for the separation column. The good thing for the separation column is I'm not aware that it's even possible to apply so much force that you can squeeze it. I don't think that is even possible. But again, only apply that much force that it grips on the column.
So it is the retention gap, right? But I'm not pushing the pin in.
You have, yeah, it is kinked.
Okay. Even here also.
Now here, can you
see it? Then I switch to the other side also.
And you save my.
That big there.
Yeah.
Small.
With the tape for the.
Gets up more.
I think they make like
If it's not getting inside, the rotator, then you will have kinked. Yeah. Still metal, which is an advantage that it cannot break that easily as pure silicon, but it's also a disadvantage at the same time.
We need to make it in the very center of the.
That at least is my recommendation. If it is a little bit more or less, not important.
You do why
So can I
sector.
Can I cut this some?
become only one side, and then length already
For the retention gap, yes, but then unfortunately not anymore
we
for
want to
separation
use
column.
because you need to
Yeah.
put the use
Yeah.
analytical column also.
Yeah.
Unless you want to.
That's why you don't get.
True,
Yeah.
true.
Now you
Otherwise, you need two tools.
think the small one is for insert from here. Insert until push half.
In fact, in the beginning, when we designed this, as I said, this is a part SGE was selling over many, many years. In the beginning, I was thinking about special, let's say, special inner inner design, so to say, that one side is smaller than the other, so that you cannot push too far. But unfortunately, production of these is so expensive that for these few we need every year. SGE didn't want to even talk to us about production of that.
Unless you like 100,000 of you, then they will do this. If let's say a few hundred you need, they will.
So we are selling a year about, let's say, 25 instruments. Each instrument needs 4.
Yeah.
So it's only 100 of these every year.
Yes.
And in the beginning, when we started with 4, we only bought the normal connector. We got some local company in Germany doing the same stuff which is now Trajan is doing.
I think I will go the other way.
Drilling a hole into the
So that
site
you'll be shorter.
and
But
welding this capillary.
cannot believe this.
Only
Yeah,
since
go down and
2019,
Eat very long.
Trajan is now producing this for us. And it took 2.5 years
To convince
to convince them and also to explain how to do it.
to make the to manufacture this.
It looks very simple,
Yeah.
but you can imagine with a big production plant, it's very difficult to introduce a new product, to change the ways how to produce it. And after that, I just gave up and said, okay, we will stay on this design. We know now for 15 years that it's fine. We do not change anything anymore.
Yes. Instead of drilling holes and welding, you never try to plastic. Plastic.
What do you mean by cast?
When you pour the
Normally, yeah. This is not. This is stainless steel. So doing this casting is not that easy. Because this first, and of course you also need again to do drilling and also CNC to get the on this. So you cannot cast a thread not needs to be cut. So this definitely needs to be done afterwards.
It has to be.
And I don't know if this can be done on the typical machines you are producing.
Well, I never thought it's so hard to make. Oh my god.
As I said, when we did it locally in Germany, I just went to a local shop near my university, and I just asked them, "Can you drill me a hole inside? Can you solder the tubing on it? Easy." But as soon as you want to have this in a mass production, completely different story. Again, it comes to the fact when you are only selling 100 of them, it's a different story when you are selling 10,000 of them. During we started with this discussion in 2016, we were not even selling 100 of them every year, but maybe let's say 50 or 70.
It's like we're asking Japan to get check off or normal phase. They will not negotiate because how many units you can manufacture in India. Yeah.
Exactly.
The same. So I think it's easier, right? See, for me not to use. You can continue. Don't cut. You still got second part. Okay.
We can
Still
use
stop.
Pinson.
Oh,
We can use Pinson.
yeah. They do the same part. Okay. You want to continue? Now, okay. Continue. Yeah, let's continue. Finish it. No, the second part. Yeah, and then connect the analytical column. You put this one in, and then this one
No, I asked you when you want to change it.
Yeah. No, no need to cut. You continue.
Oh,
Yeah.
okay.
That's the
This one you screw. You screw this one, then at least we finish.
So what are we trying to do now? To do a second connection
Analytical column.
on the analytical column. You do not need to connect at this stage. Just leave that now empty. We are done on this one.
Oh, leave it empty.
And now you are doing the same for the other. Exactly the same thing, the same way. You can just leave sticking it out for a few centimeters and then you are cutting afterwards. Just let's say 5 centimeters or whatever. Leave it out of the column
The
of the
separation column is easier, I think, because the end of already here. Shows you the understand.
Before cutting, I will say a few words about that, but for now, just put the ferrule on it.
This guy shouldn't get on the one. He already put in a rule. So
Now, what you can do now, just install it in this way. But the ferrule should be in here. Yeah. You can also just put it this way, and then you can just put it through there. And just do it this way because we can cut afterwards.
this one no need the scissors.
No, because you would need a pin with 0.25 diameter, which in fact is just a thin wire, which is so flexible that it doesn't that it cannot fix anything, and you cannot over tighten that.
This is so metal one. Yep. This is a good
Oh,
point.
then why won't you get over tighten? Because it's still metal.
Yeah, but
Diameter very small.
the thing is the diameter is much smaller than these ones. The force you need to tighten this one even more is so much higher that, at least from my experience, it was not possible. Typically, when you try that, the first thing happens is that you are breaking this connection here, and then you are just ripping off the tool.
Of the track.
Yeah,
Try to
yeah,
come out.
yeah. The torque is so high that you will just, when you look onto the tools, these are still produced by one of our local companies near our facility. You see that there are just 3 little dots where this is connected on this tool. So when you use too much force,
You come out.
you will just destroy the tool.
This is expensive, huh?
This
This is expensive.
For troubleshooting purpose, do you sell or it comes with maybe without this one, but just for union to join them up for supply?
Why?
Maybe I want to bypass the
True.
yeah,
True.
just
But
for sometimes for that.
what hinders you to install the tool inside?
Or just put it inside.
Okay, I think.
Okay.
We are doing it in this way. We are just installing the tool then.
Okay.
You push more.
Now, as I said, have you cut it already?
Already.
So, you have cut it afterwards, right? Yeah, then it's fine. Then it's fine. Do you?
Okay.
Yeah, it's okay in this way. You can even do a little bit shorter, but only to explain why it is in this way in the picture. As I said prior to lunch, it would be fine when you just have a very little overlap.
One end.
Just one millimeter would be perfectly fine. It's only important that the separation column penetrates a little bit into the retention gap. So they must not be installed this way. It needs to penetrate. It's now easier. This is now the exact same view you will have inside a GC oven. When you are replacing the retention gap, so you are unscrewing this side, you are always seeing the end of your separation column. So it's much easier for a new retention gap to be installed because you can see the separation coming. Yeah, it's much easier. It is perfectly fine from analytical point of view to cut it that you cannot see it anymore. But it's much more difficult to install than a new retention gap. Because most likely you need to unscrew also on the top side to install this side first and then this side as a second. And it's easier when you can see this end, easier retention gap installation. Okay, that's all. Why we recommend to have the separation column a little bit sticking out of.
So the analytical column a little bit longer, it will not affect the evaporations.
No.
Because it's so narrow.
True.
So the tubing.
Yep. Yeah, it doesn't need to be so long, but as long as you can see it, it's fine. Because it just makes it easier.
The joint, which already damaged.
I you want to try it.
Got it one. I will already. Okay, I have my own. Can do that. But need to find the damaged one. Oh yeah.
What you need to, what you thinking?
You want to build his own tool.
But Shimatsu is also a vendor for these union here.
Yeah.
So you should have them somewhere around here.
In other instrument.
The T joint.
No, only the
So it's a normal one. It's not so stuff.
No, this is Trajan design. This is SGE.
SGE.
So as you know, or as you don't know, I have it in a presentation. So if you are interested, I can show you. SGE, so scientific glass expertise or something like that, or experience, was an Australian company producing syringes, also Ziltite, Silflow, and all that kind of stuff. This company was acquired 2011 by Trajan, and it's now Trajan. So SGE, the company, very, very old. I think they were.
So no longer SGE now.
No. SGE is since 2011 Trajan, and all products you are seeing are initially SGE products. So you might still see SGE also on some of the cardboards or something like that. But SGE, exactly the same as Axel Semrau, was acquired 2011 by Trajan. It's now Trajan, but of course still the same crew in Australia and also the same products. Okay.
So now just connect to here.
Yeah, in fact, you would now connect inside a GC oven to the C pieces. Yeah. So since we are 11 people here, is everybody confident in doing that? Because normally in a training in Germany, everybody needs to attend that. Are you sure that you can do it by yourself, or should we do it a few more of the times?
So we can always play the machine.
Yeah, we have it here.
You can play on the machine here, but your colleague maybe not.
I think let's do the overseas one. Maybe we can do it at our own time.
Exactly.
You cut and then you do again.
Yeah. That's one of the big advantages when you have your own instrument. But when you don't have one, you need to play at the customer side.
That's why I was asking. We have extra space in our balls to practice.
Yeah. Yeah, unfortunately.
So now
But you can also, if you like, I have plenty of these, which, as I said, do not have the correct diameter. But when you can find with the correct diameter, feel free to install this.
you can use this cheaper.
This is from my own salary.
Oh, sorry.
It's fine. just means you need to sell more instruments.
Elton?
Pressure very fast.
Your industry don't have this yet.
Oil.
Oil is packaging lah, packaging. The market is more
Yeah, he has to
You can use both.
Just going to buy a
Both can use for trade.
Yeah, I have two detention gaps and two separation columns.
You want to try?
Yes, try.
Is already used.
find the current size of the.
No, I think you use the new one. You use the.
Sorry, I use this.
My lab is
Yeah, what about the?
Around this degree. That's how I tighten up. Like that. So one of them is maybe around.
This one that is 32.
Otherwise, you will have leaks, and I can imagine it's much more inconvenient when you need to tighten again after maybe 3 or 4 injections, and again and again and again. So what I can promise to you is when it is tight one time and you do not move anything, it will be tight also 100 years later. And when you are used to that procedure, when you have done, as you have right now, I've done it a few times. I know it's a little bit more complicated, but not that complicated. Especially when you know which type of metal terabytes you should use and which are the intended ones. When you keep all installation length as intended, you never need to think about that. That works just out of the box all the time. Any questions regarding GC columns at that point? Okay. So one step further, let's now look on how the sample even got into your instrument or in our instrument. That's the transfer valve we are using on the PAL, which is guiding our liquid from the HPLC into the GC. You can also see what I was talking prior to lunch. These are the so-called peak sleeves when you want to connect a few silica capillary or in general a 360 micrometer capillary into a 16 in 1/16 of an inch valve. Therefore, we use these small sleeves. They are just used to provide the correct diameter from the inside and from the outside so that we can connect those capillaries to such kind of a valve. This is a special type of a valve that's a multi-selector valve, and it looks a little bit different when you are not used to that. I just put in here the flow path of that. But basically in standby position, our liquid from our UV detector. So we know that we are injecting into our sample loop. We have our separation on our silica gel column. Everything is exiting our silica gel column, entering our UV cell so that we get a UV chromatogram. And everything from the UV detector is coming up to this center point. And this center point in normal configuration, that's what's shown here. That's the center point. When you turn on the PAL, is connected to this top point. So meaning everything exiting the UV detector will just guide it to your waste. Okay? As soon as we want to transfer much or more, which as we have learned is a time-based operation. At 2 minutes, we have seen that MOSH is starting to be transferred, and at around 4 minutes it's more, which means this valve is turned at 90 degrees, which means we are turning this thing here from this connection to that connection to guide our liquid through this capillary into our GC channel 1 or FID 1. When the transfer time is finished, the valve turns back to the waste port. We can then flow again into our waste port. And as soon as the more time emerges, this valve turns to the other side to connect these 2 points. that we are then flowing into our GC channel 2. So far, so good. These capillaries here, as they are connected, let's say somewhere here, we have exactly the same T connector that we are using inside a GC oven. So this T connector, as I have, I think that was on the very first slide, is connecting the eluent of our HPLC system with the carrier gas. So in this T connector on top of the instrument, we are mixing carrier gas and liquid. When we are not transferring, it's pure carrier gas, of course. Any idea why we still have here restriction capillaries? These are exactly the same size and the same length as on the solvent vapor exit. Any idea why they are there? Or why they are needed?
Depression, resistance.
In the end, yes, but I could also put a plug in here just as an idea. Why can't I do it in this way? When the transfer is active, through this capillaries we have liquid exiting from the HPLC. So pure liquid, no gas, just pure liquid. When the transfer is finished, these capillaries are still full of liquid, which again penetrates uncontrolled over time into our carrier gas, which again gives us an unstable baseline because it's still 100% organic solvent. And as an FID unfortunately shows us any organic solvent, we will see liquid penetrating into our GC column. We will see an unstable baseline. We cannot predict how long it takes to empty this line because this is then done purely by diffusion. But to prevent that, when the transfer is finished, so when this port turns back to waste, our carrier gas that is connected with the T connector is pushed backwards through this capillary and pushed out of this bleed gas flow line. It's more or less the same idea as on the solvent vapor exit valve. It's basically the same idea. As you can imagine, when this one is blocked or clogged, also giving us a very nasty chromatogram. Also, this one here is just giving a very small gas flow. So also at this exit and this exit, you have permanent hydrogen exiting the instrument. Just a very small gas flow. It's only a few microliter per minute. So nothing compared to the gas flow we are using for separation. But it's needed to have a steady bleed gas flow, so to say, so that we are preventing that the liquid which is inside this capillary will be diffusing in our GC separation.
So meaning during transfer, whatever liquid can go into the retention column, you will do it. The remaining in this transfer line,
yeah,
will then back flush.
Exactly.
Out.
Exactly. Just by the pressure of the carrier gas itself. What you will see when you are in front of the instrument, after a transfer, when a transfer is finished, and we are turning the valve back from here to here, or from here to here, as the carrier gas pushes the content of this line backwards, you will see always a small drop of liquid exiting this capillary here. This liquid is the content of this capillary.
But how can you bring a carrier gas push from your T joint towards this capillary?
That's what gas is doing by itself.
Because your retention gap column diameter is so big, I thought everything would just go down to your.
Unfortunately, or let's say, unfortunately not. So this is our open ceiling, so open top. We have our T joints here. So we have hydrogen coming from the side. we have our retention gap, and we have our capillary from the top, just to keep it simple at that stage. In normal scenario, so no solvent vapor exit opened, just normal operation, the carrier gas flows from here into the retention gap. But because of the end of this capillary here is connected to our valve, it's this one, and then we have here our restriction. Also part of the carrier gas will move up through this capillary, exiting out of the fusilica restriction. Of course, it will mostly flow into this way, but but closed.
Close or
It's just what gas is doing by itself. So gas always wants to flow from a high pressure to a low pressure. And since the restriction capillaries are not closed, they allow still a very low bleed flow. You will always have gas exiting this way. Not much, but it's enough to discharge these transfer lines backwards to prevent diffusion of the liquid inside our chromatographic system. Therefore, you have always, a few seconds after the transfer is finished, a small amount of liquid at the end of these capillaries. When you are there in front of the instrument, and we can do that afterwards if you like, if you want to see it by yourself, you have always one drop of liquid, which is the volume of the inside of this capillary.
and this capillary is not shifted.
No.
You're not afraid that you will have carry over for the next.
Good point. Good point. You need to be afraid,
Need to be.
but I will show you how to fix that. Up to that point, everything clear, at least for now. This valve has, in fact, this special configuration that when it's in standby, that these two ports are still connected. So that we have the possibility to have a backflush without any additional valve or something like that. That's just because of the special design of the valve. The fifth port, open here, is another channel that typically is used for our frac and collect tool. So I think that's also installed there. When you install at port number 5 your frac and collect tool, and you are switching the valve from waste up to port number 5, you can just move in the same time your tool to a vial and collect whatever you want inside the vial. And another option we sometimes offer, not that much, is having a second GC and to use that exit as a third channel. It's, for instance, when somebody wants to have an instrument where GCMS is also possible. So that you have much more FID on the first GC, and potentially you could put a GCMS next to it with a longer transfer line. It's not a big issue with a longer transfer line than into a second GC.
Second injection. I need to do second injection.
Depends on what you want to analyze. For instance, you could guide MOSH into the FID, but more into GCMS. Of course, you need to decide before. You cannot divert into FID and MS at the same time. Then you need to do it in the same GC often, and you need to have a split inside. Okay.
How about the valve number 8? Number 8 is empty.
Number 8 is empty because it is the connected port to our waistline. It doesn't make much sense to connect anything there. Therefore, we are typically providing a plug on this port. Unfortunately, you cannot use it for anything useful. As you can see in normal operation, when the middle port is connected to the top, port number 8 is completely blocked. It cannot do anything. Regarding our peak sleeves, are you all aware how to install that? Any problems in the past? So the idea is basically we are installing it into a Vichy valve. So HPLC valve by the company Vichy, which means we are using a nut from the company Vichy and import also a ferrule by the company Vichy. We have our peak sleeve, which is providing our guidance from 1/16 of an inch down to 360 micrometers. And by installing everything, in fact, you are just pushing everything inside the valve. You are screwing, and then you are providing a leak tight connection for the fused silica tubing. When you do not over tighten, you can open all the time and install another capillary. I suppose we will do that in front of the instrument so that you know how to do a complete new one. But effectively, what I put in this slide here is when you are having a new peak sleeve and pushing your capillary fluid, there's a high chance that you will have peak particles that inside your fused silica capillary, potentially blocking it. So therefore, always advisable, completely through, then you are cutting like you would install a column inside an FID. Basically the same. I think it is, when you are thinking about it, quite clear, but for customers, maybe not. Therefore, I just put it here on the slide. But we can do it in front of the instrument just for convenience. Coming to the question how we are preventing carryover. This is how we are installing our transfer metal capillary and our retention gap on top of the GC. So this is the T connector on top of the GC. And you see that the retention gap is installed exactly like on the other connector till the middle, but the metal capillary is penetrating very far into the retention gap. Any idea why we are doing that? So as we have learned in the GC, we have stopped the capillary of the separation column here. But for this capillary, we are installing it very deep inside our retention gap. Any idea why we are doing that? It has to do, you have already said it, with the temperature.
No idea.
Really preparation.
Okay, so that would be how you would install it right now, because this is the way how we are installing it inside the GC oven. When now your liquid drips out of this capillary and is mixed with carrier gas, yeah, so we have our spray out of our capillary, we are mixing it with the carrier gas during our evaporation time when the solvent vapor exit is open. We have unfortunately also capillary forces that sucking up liquid backwards on the sides on this side of the capillary. That's unfortunately just capillary forces. So now liquid in very thin areas is tending to climb up. which also means that our compounds inside this liquid are doing the same. What's the consequence of that? Contamination, and you have used the correct term already. Carryover in the range of 1 to 5%, which of course is quite much. What we are doing instead is, of course, we cannot prevent this. So this will happen all the time, regardless where I'm installing my capillary. But when I move it far deeper inside the retention gap, and then it happens here, that we have this liquid on the sides of our retention gap in this space here. This part of the GC in the end of the chromatogram has 370 degrees, which means these compounds here, by the carrier gas coming from the top, will be moved. So we have carrier gas coming from the top. They will be mobilized and just be flushed out of the instrument. Therefore, the retention gap is installed like the one in the GC often, but the metal capillary is penetrating very, very deep into our retention gap. In fact, it's not important how deep, it only needs to be in the very hot area in the end. And easiest way to measure, it's not 12 centimeter because you need 12 centimeter, but this length is 12 centimeter. So when you are installing something, you have most likely this box next to you. You do not need to have something there. You can just use this length. This is just 12 centimeter, even 10 centimeter is fine. But nobody, at least from our service engineers, typically they don't have ruler or something there. It's just we notice this is 12 centimeters, and then it's basically just measured from the top here. 12 centimeter is penetrating far enough into the GC often, and it's fine. Even if it's 13, 15, 16, 20 centimeters, not important. It just needs to be in the hot area. When it's too short, this is also one of the tests during the type 3 acceptance and site acceptance tests. There's also test for carryover. When you would install it too short, you cannot pass this test. In fact, we are just checking it by injecting the retention time mix. As we have learned, it has 11 compounds or something inside. I don't even know, but up to C50. And when you would install it very shortly, you would have quite high carryover for C50, because this effect is, of course, dependent on the boiling point. Very light boiling compounds, so all our volatiles, not a problem, because most likely even on top of the GC, you have still 80, 90, 100 degrees, something like that. But the very high boiling compounds, of course, need the high oven temperature to be sure that you can flush them out. Okay?
So whatever left on the top is fine. The metal capillary.
You mean this one here?
Yeah.
In theory, yes. In practice, it just doesn't look nice when you have 10 meters of capillary there. So therefore, we normally install it and have a nice length to our transfer bed. But if it is 2 centimeters longer or shorter, absolutely not important.
But I mean the compound inside the liquids travel inside.
That's fine.
It's fine.
Yes. Because of the back flush, we are just pushing anything out. And what you do not need to forget,
The liquid, that's why you know.
our MOA chromatogram on the HPLC side once again. Let's only focus on MOSH. the liquid inside this capillary is the liquid at the very, very end of this transfer, which is basically only pure solvent. The idea of a time window, of course, is mosh needs to be inside here, and the end is designed in a way that it is basically pure solvent.
So
Otherwise, you are cutting inside your mosh fraction. So therefore, the time is designed in the way that it flushes the inner side of the capillary basically by itself. But during the evaporation process, we have always this capillary force thing, and all of our compounds basically could stick between this area here. So this cannot be prevented, unfortunately. When you're doing something like that with a syringe in a PTV or in an MMI, it cannot happen because the needle of the syringe is much thinner than the diameter of the liner, most likely. When you go to very thin liners, it's basically the same, but you are putting out the syringe afterwards. When you would keep the syringe inside, it would be exactly the same. That's one of the disadvantages when you have such a pre-configured connected system, because I cannot remove this capillary after each injection compared to a syringe. Okay. What I did not talk about yet, that's in bold letters, the last sentence there. Unfortunately, our transfer capillary is a very thin one, so 360 micrometer OD and 75 micrometer ID needs to be cut quite nicely, because otherwise, let's just do it this way. We have cut it that when our liquid is penetrating through, it will spray in a 90-degree angle. That can be done, unfortunately. And when you spray into a 90-degree angle into your, can I go one back? Yeah. Yeah. When you are spraying in a 90-degree angle into your retention gap, it means it penetrates even more to the top. Therefore, when installing a new transfer capillary, you always need to check that you have a clean cut so that your liquid basically is going this way. Otherwise, again, you will not pass the site acceptance test because of carrying over.
The 1000 ppm of
What we do is basically very simple. You take this capillary out of the T connector, and you are activating a transfer into MOSH or MOA. Then it will spray out of this capillary. Because you can see the spray, and you can even cut while it is spraying. Then you cut, hopefully, only one time, that you have a nice spray. It's again coming a bit to the fact if your tools are nice, when they are not sharp, of course you cannot expect a clear cut. And when you're cutting very slowly, then again you will have a spray which will do something like that. So it's again a fast cut. You could even use just regular scissors. So when you take a scissors and cut fast, you will most likely have a perfect cut, because this is a very thin capillary, and you can just take some normal scissors, cut, and then you will most likely have a nice spray. But this is something, for instance, when we're installing these capillaries, what we are checking, because it's quite fast for the check, but you then can be sure that you will not have any issues with carryover. Again, it comes all to the small things. So in fact, I know it's many things, and they all have smaller impact. But in the end, when you do not know about it, you are not sure where you are looking for a mistake or a spot or whatever. And when this is boring for you, just say it to me. We can go faster over these topics.
We might not know what we don't know. We might not know what we don't know, so it's best you.
Okay. So just for explanation what the instrument is doing on which part, it's now basically coming to the auto-sampler use case. As we have already learned, it's completely doing our sample prep. So we can completely ignore LC, GC, and also transfer, because sample preparation has nothing to do with any injection. So it's basically only this part here. This is what we have briefly discussed during the lunchtime. In the end, it is only HPLC, GC, and sample prep. When you can separate this in your mind, and you are not so overwhelmed that it is a big instrument, very expensive, and all that kind of stuff, it helps when you are looking for a specific issue. Of course, we have a quite complex valve switching stuff. This is all controlled by the PAL. And of course, we are injecting in our injection port, and also collection, as I have already briefly pointed out, is done also by the PAL. So in fact, the PAL is doing injection, collection, and also all the switching, HPLC switching part, and sample prep. And now, yeah.
If we need to do all these simple preparation, we not open switch of the LC and GC can do.
Not sure if I get this.
Sorry. If we need to do all these simple preparation,
Yeah.
we not open all switch.
Yeah. If you, I'm not sure if I.
LC, GC,
No. When you only want to do sample prep, it's totally possible. You can just stop before injection.
And there's a method that only run the sample prep, right?
In fact, the method we are using is only sample prep, which means when you are not putting injections into the same sequence, you will end in the small vials, and that's it. We are also selling. We have also sold that, I think, up to 5 or 6 times. Only this part. So when customers already have LCGP instruments that can only inject, then you can also sell standalone sample prep. That it is only doing subunification and epoxidation and this kind of stuff, and it ends in the small vial. This is sometimes cheaper for a customer. For instance, we have customers that have 6 Mojmoa instruments, but only with the basic injection unit. Then they are doing sample prep on another instrument, taking the vials and putting them on the 6 instruments. We have sold also such solutions. They differ a little bit from this configuration because we are also putting a kappa decapper on this instrument. Because as we know, we are penetrating into the 2 milliliter vials, and as soon as they are penetrated, they are not leak tight anymore. So we are evaporating the content of our sample. To prevent that, we are in this configuration opening the vials, putting the liquid inside and closing them again. Therefore, it's safer, especially when you are not always in the vicinity of the instrument, that you can just start your sequence, come back after 2 days or whatever, but you have perfectly tight small HPLC vials that you can then put on your thermal instruments. Also fine, and we have sold it in this way. Okay, now I assume it gets a little bit complex for the ones of you that are not aware of HPLC switching valves, because we will now slowly look through our switching part, because of course part of the training is also that you understand how the flow flows, that you are understanding which valve is having which task, and also in which state it is doing which operation. So for now, let's look onto a configuration without aluminum oxide cleaner. This is the basic configuration. You cannot make it easier. You need this type of 3 valves. And just to mention, this is what we already seen. The sample loop, of course, is independent of our, let's say, our method. The automated workflow with all the sample preparation stuff has a bigger sample loop than the standard configuration where everything is done manually when it comes to the sample prep. But basically, the first valve is only for injection and to get our sample somehow into our sample loop. So in standby condition, we are not injecting anything. Let's see how the flow is going. Let's see how the flow is going. Our HPLC pump is at 100% hexane, just with a small flow. So normally 50 microliter per minute. We are flowing to port 4. We are flowing through our sample loop to this valve, which is basically just to activate the backflush of our HPLC column. But in the normal scenario, it's flowing this way through the silica column, back to the valve, to our UV detector, out of the UV detector, to the middle port, into the waste. So far, so good. During injection, only... Everything clear? Okay. During injection, the only valve that's switched is essentially valve number 1. So just to show you, we are switching, and a typical HPLC valve is working in the way it switches the valve or the rotor skin inside for 60 degrees. Because you know, the circle has 360 degrees. We have 6 ports, which means to move this groove from here to here is 360 divided by 6 means 60 degrees. That's how an HPLC valve is actuated. We are injecting from the top through our sample loop, and everything which was inside the loop is just put out of the valve. Next operation would be the valve is switching back, and we are starting our nominal flow rate with our gradient. So not important how the gradient looks like, just put that also in here. That's also by the color what you can see. We are now flowing with a certain amount of dichloromethane. No valve has been actuated. After 2 minutes, after the void time of our column, we are activating this valve, which means we are now flowing into the first GC channel. After MOSH is finished, we are switching back. Then a little bit later, we are switching to MOA. After a little bit later, we are switching back. Easy, I think. Then, essentially, our HPLC run is finished when it comes to separation. We now only need to make care that we are backflushing and re-equilibrating our column. This is done by actuation of this valve. We have switched in the meantime to 100% dichloromethane, and we are flowing again through our sample loop, just now the other way, through our column. and now directly into the waste bin, because I wanted to make sure that we do not push all the junk through our UV cell, because otherwise it would need to go the same way here and could only exit on this port here. But that essentially is information that we just do not need. In this time, as you can see by the color, this is a blocked port. Every liquid inside our UV cell is just not flowing anymore. It's just stopped, which means regardless of what is inside our UV cell, we will get from here to here a stable baseline. What we have seen last week, when this, for instance, when we managed to get perylene inside the UV cell during this time, we will have perylene staying in the cell until we are reverting the flow again. It's just because the liquid stays inside our UV cell. Now back into normal direction, 100% hexane to the end of the chromatogram, basically to get a stable baseline again. There is one flow drop here from 0.5 to 0.3. We will talk about this a little bit later, why we are doing that. But basically, it's now only necessary to get back a baseline that is at the same height as in the beginning, because then we are sure that we have only hexane inside our instrument. Not that complicated, I think. Okay, for now, let's keep it this way when it comes to the HPLC flow path, and let's have a look what options we have on the PAL regarding configuration. The very basic one is only an 80 centimeter RSI PAL. That's the version that cannot change any tool. Of course, it's much cheaper, but it cannot be updated to frac and collect, because the tool needs to be changed when you want to do injection and collection. Therefore, this is much cheaper, but of course, it has much less configuration possibilities. Can be upgraded. As you know, the difference is only the arm, but I think it costs then in the range of 20,000 euro when you want to update. So whenever a customer plans in future, they might want to use frac and collect, it's cheaper to decide for an RTC, even if it is only 80 centimeters, but it is cheaper this way than upgrading later. When a customer only wants to do MCPPA epoxidation, and basically we just do not have any customers that only want to use this method, we also have a 120 arm there. But basically it all is nowadays for the automated workflow that we have either 160 or 2 meters. The 2 meter version basically only is needed when you need more trays, that you have more space for your sample vials when you want to have a capacity of 60 samples instead of 30 samples. We have our evaporator and of course more trays and space we need for the chemistry.
Sorry.
Yeah.
Just a few, just based on last week's conversation, you taught us, right, the throughput for the analysis of the degree, right, per day. So even we have a longer arm, we still cannot analyze more than 30.
You cannot be faster than that, but many people want to work unattended over from Friday to Monday. So not many are going into the lab only to put more samples on the instrument. So it's basically when people want to work unattended over a weekend so that they can put up to 60 samples on it. And then on Monday, everything is done. But yeah, you are right. We cannot be faster anymore. It's only for the capacity. And it comes down to this configuration. So it's basically always looking like that. that in fact is now on top of an edgeland GC, but it's not important what GC is below the PAL. It always looks like that for the 30 sample option.
So the 2 meters one will have more
Like that. Yeah, so we need more space. So we have more of these metal racks, and in fact it's then not only 2, but it's 4. It's then 4 trays, so that we can start on a tray with 60 samples, 60 for the second stage and 60 for the third stage. It's basically the same operation, it's just the space, unfortunately. And now going through what we have on the instrument. We start on the left side with our wash module, which basically is there to clean the syringe, but it's also used to supply solvents for the chemistry behind, because we need hexane and we also need water, because both is needed for the chemistry. So it's a combination then of cleaning the syringe, but also a convenient way of supplying high amounts of liquid, because when the instrument is used 24 hours, we need around 1.5 liter hexane per day. Yeah, that's quite much, but when you would do it manually, it would be even more.
The total, the hexane amount 1.5 liter is not total for like 33 samples.
30 samples, more or less. 1.5 liters.
For mobile phase and also the wash.
Only for the sample prep.
Only sample prep.
Only sample prep.
Including the mobile phase.
Mobile phase compared to that is quite little. It's basically, as you know, we are doing everything with the same syringe. We need to clean between all the steps, and I think we need for each sample only, I think it's 5 milliliter added as a solvent. So let's say it's basically 10 milliliter as solvent supply for each sample, which means more or less 300 milliliter for a sequence of 30, more or less, and the rest is basically only for cleaning.
Oh.
That 1.2 liters only for cleaning.
1.2 liter for cleaning.
Yeah. Because I cannot, as you can imagine, I cannot just use a syringe twice. And I found no way to work or to improve. But it's again compared to manual sample prep much less.
And this need to be a super hexane.
Unfortunately, in the end, it of course doesn't need to be a super solvent. It only needs a solvent where you are sure that you are not having moshmoa inside. And we will learn later also how to check this.
During the 24 hours operation, right? On all the reagents here, besides the vaccine, which one will breathe running out?
In 24 hours, nothing.
Nothing.
It's basically, I think when I designed it, every bottle is enough for 24 hours of uninterrupted operation. For the 60 sample version, of course, also. Then it is for 60 samples without any interaction.
But this standard amount of hexane, is it in the sample prep? Because in the sample prep, we also use that amount, right?
Yeah, no, this is what you are doing manually before.
No, I mean like just how you say.
Yeah, 10 milliliter is what you are adding manually.
Manually.
The PAL is doing 5 milliliters in the second extraction. And let me think. It's basically then only 1.5 milliliter at the end when it comes to what's used for that. So it's
6.5.
6.5
plus 10.
plus 10,
So
but
it's-
10 is manually done before. But when we calculate that with all cleaning steps, it's basically it was 1.5 liter for 24 hours.
So the 1.5 liter is to exclude the 10 ml manually. Exclude, right?
Excluded.
Oh. So, 1 day example. 10 ml is 1 division. So 1.2 is a small machine. And then you have another 300 just manual.
So we have our module here for supplying hexane and water. We have our agitator here, which is basically used for all chemical reactions, 65 degrees. In there, we are doing saponification, also epoxidation. We have then, let's just jump to this area here, 30 samples where we put our, we have 30 slots where we are putting our samples inside. Since we are doing saponification, the first vial, we need to transfer the liquid after saponification from here to here. Therefore, another 30 positions. We are doing a second extraction as we have learned. So new hexane on top. These are our 5 milliliters. Again, extraction. Then we are putting that in here. And after evaporation in our evaporator, these vials are brought back into the agitator for epoxidation. After epoxidation, after quenching, so meaning the use of sodium metabisulfite, these vials or the upper layer of that vial is transferred to the third vial. Again, 30 positions. Yeah, so we have 30 positions again. And after evaporation down to dryness to get out of our chlorobutane, because exactly like chloromethane, one chlorobutane must not be in the liquid, otherwise we cannot do our separation on the HPLC column. After this is completely evaporated, we are putting 1.5 milliliter hexane on top. And this again is then transferred into the small vials where we have more than 30 positions, but these vials are then injected into our HPLC. That's what we cannot see in this picture. This is how the instrument is designed. So we have talked about that. Empty vials here, empty vials here. We have already done this step here for the sample prep. We know that this one here is our quenching reaction. This one here is our quenching reaction stuff. So sodium metabisulfite. I'm just wondering that somebody put other names on the bottles, but it's the one correct here. So quenching reagent, chlorobutane for the epoxidation, ethanol, basically also for cleaning of the syringe, because as the syringe is transferring water and hexane, we need also a solvent with an intermediate polarity. So therefore, we need ethanol, and also to get sometimes a better layer separation inside our sample vials. We have our reagents for epoxidation, which is formic acid and phosphoric acid. We have hydrogen peroxide. We have our centrifuge, our evaporator, and we have a keeper solvent. We have not talked about that much, but this is basically something the instrument is using to prevent evaporation of the highly volatile compounds. Because as we have learned, normally when you are evaporating, you are also evaporating all of your volatile compounds. You cannot prevent that when you are not having a retention gap. In the retention gap, this is done by solvent trapping and all this stuff. But in a vial, you cannot prevent that. The easiest way to prevent this is to have a liquid mixable with your sample and your solvent, which has a very high boiling point. Because in this liquid, your compounds will stay and cannot be evaporated. Therefore, we have here a boiling solvent called a keeper solvent, which has a boiling point, I think, of around 500 degrees. This, in fact, is some kind of a plasticizer. Plasticizers, as the name say, are there to make things smooth and all that kind of stuff. And they have the advantage, they have very high boiling points while still being liquid at normal temperatures. And it's completely mixable with hexane and our sample matrix. So this is used to trap our compounds during evaporation. And it's effectively polar, which means when we are injecting all the stuff, the keeper is removed by the HPLC column. Okay. Centrifuge is clear, and we have something called dummy vials. I think it makes sense to have a look onto them on the system and why we are needing them. Just in case somebody wants to do the old MCPBA epoxidation method, it works on the same hardware. And for convenience for you, I just put all the stuff where the vials need to go. We have done this last Wednesday. We do not need this area here. All samples are going through this slots here. It's a little bit related to the fact that we also still have customers on the 1m20 instrument. And the 1m20 instrument doesn't have this slot. So we decided to have this method essentially backward compatible to the old hardware. Therefore, 30 samples can be epoxidized with the old method here. We're starting here. This one here is completely empty. This vial here is replaced by our MCPBA. And this vial here can be replaced by a mixture of sodium thiosulfate and sodium bicarbonate. But it can be also used, and we did it last week, you can also stay on this configuration. This is only in the beginning when I first developed this method, because this method was part of my PhD in 2016. I was not aware that it's easier when you just use meta-bisulfite as quenching. Therefore, I came up with this mixture. Unfortunately, it is needed as a mixture, so you need to mix two compounds, because unfortunately, as a side reaction, thiosulfate is forming elemental sulfur, which means when you are not putting something alkaline inside, you have some kind of a yellow goo inside your sample, which is just elemental sulfur. Fortunately, elemental sulfur can be dissolved in hexane and is giving a nice peak also in your UV chromatogram. It's not disturbing anything, but everybody was asking why there is a peak inside the chromatogram. Because it basically it's basically a peak that was between Mosh and Moa. This is basically S8, so elemental sulfur. It doesn't do anything, but it looks shitty. Yeah, so therefore, in the beginning, I needed to find out what is happening there, and that's unfortunately one of the side reaction of sodium thiosulfate at acidic conditions. It forms from here, from the sulfur in there, you get elemental sulfur, which is not possible on meta-bisulfite. Therefore, you might see literature where you have this mixture, but you can do it also just with that.
So it's the NCPA option your FAT is using metal-based solvent?
Depends a little bit of our service engineers. Depends on if they are still using that one or this. But at least I said everybody they can use that. But sometimes people are afraid of trying new things, and might be that they have done it on this configuration. But in the end, it's with the actual Kronos method. You do not need to change in the method anything. It's not important. You can either put that one or that one in. You do not see any difference.
The thing is, what's the function of the formic acid?
Formic acid?
Yeah.
Do you want to have an answer now or when we come to epoxidation? Okay. Yeah, that's normal. That's normal. No, that's normal. It's because it's a very highly concentrated solution. And you have also, I don't know if it is elemental sulfur. I probably think it's some sulfur compound giving you this slightly yellow color. But this is normal. But it should have this color from the beginning, right? Or is it turning over the time? I think it has this color from the beginning, and I think it should also be here on the instrument having this slight yellow color. That's normal. Yeah.
If turning, it will be not normal.
Turning is not normal.
Turning is not normal.
Turning means there is some active interaction there, but it looks slightly yellow from the beginning. That's normal. And be very, very careful. You cannot use this solution for the automated workflow. Why?
It's just to try.
We explore.
Maybe you even want.
The thing is,
Beta by supply. Yeah, see supply.
any idea what this is giving? So we have a highly acidic solution containing formic acid and also phosphoric acid, and we have sodium bicarbonate. So this is an acidic base reaction. So this is effectively baking soda. Baking soda plus, let's say, citric acid, as you do it in the kitchen. It's forming CO2. Yeah, so you have a high pressure inside the vial just by the neutralization of the sodium bicarbonate, which is reacting with the formic acid or the phosphoric acid. And this additional CO2 is deforming the septa. And in this configuration, it will very likely stop the sequence because our method is not aware that you have such high pressure inside the vials, and even the venting process is not effective anymore. So the septa will be deformed, and as you know, the PAL is transporting samples by magnetic contact. And when the septum is looking like that, you cannot do any transport anymore. Unfortunately, also that happened to customers, that they were switching between the methods, still having the quenching reagent in this configuration, but switching to that configuration, and then they were trying to phone us why the sequence is stopped. And in the end, it's just by forming baking soda plus acidic conditions is forming CO2.
At least it will not exist.
Explode, not.
You never encounter explosion,
I have encountered also explosion.
But not at this.
I have. And also customers have.
because of wrong chemical or
Huh?
because of wrong chemical or
Because
too much
of
pressure?
wrong chemicals, not so much. Because of they were not aware and did not understand what they are doing. But you need to understand this is heavy chemistry we are doing here. And it always needs to be applied in a safe way. Especially, I was talking, I think, last week about disposal of all the stuff. When the people are just pouring everything together and you have an explosion, don't blame me. Yeah. Yeah, that's this configuration. Basically, you need to switch a few chemicals, but then it is perfectly fine to use, as we have done last week, to use both methods on the same instrument. Honestly, nowadays, I'm not aware that anybody is doing that, but it would be possible.
That's a topic of what you mentioned about waste. So for all this, if you're going to throw at the end of the day, do you have any quenching recommendation?
You do not need, because
Is it quenched?
it is quenched.
So there's no issue with, I want to mention, throw everything.
You can. In this state, you can. What you could buy, you can get so-called peroxide testing stripes. This is a stripe, a small stripe, with some chemicals on top. When you put it into a solution, it turns the color blue, normally blue. When it is not turning blue anymore, you know there is no peroxides anymore inside.
Is it fine? Previously, how I quench is I just leave it 24 hours. But
Yeah,
the next day I
yeah,
So it's fine that way also.
absolutely. But as I said, we have customers that are just disposing the vials in this state, so closed into special waste bin. Then everything is just disposed. We have unfortunately also customers opening all the vials, reusing all the metal caps. So they are pushing out all septa. They are reusing all the metal caps. They are pouring everything inside the vials into a dedicated waste bin. Then they are putting all the vials into a dishwasher to clean them and to use them a second time. Unfortunately, this is one of the main issues when you have explosion, because the detergents doing the dishwashing process will affect also the quality of the glass. When you do that multiple times, the glass is not stable anymore, which means during saponification, there is a chance that the glass will just break. It's not an explosion, it's then just a broken glass. But we will talk about this a little bit later. Yeah.
For the keeper just now, I noticed that you mentioned only 50% of the problem. Is there any specific reason for that?
Yeah. The keeper, as it is a very high boiling solvent. You can imagine when you have a completely full vial, you have the complete needle, the complete outside of the needle, then you have this gooey liquid. And the top of the needle cannot be cleaned anymore. Therefore, it is not a big issue because the keeper is not contaminated with much more, but it looks very ugly very fast on the instrument because you always have spots where you have this liquid which just doesn't look nice. It's not because of chemistry. Even when it would be completely full, I don't think that it has negative consequences for the analytics, but it looks, from the cleanliness point of view, looks a little bit nasty. Therefore, since we only need 70 microliters for each sample, even with half a vial is around 10 milliliters, you can imagine how many samples you can do with that.
So what you mean, you will drip all over the place?
Mm-hmm. We have already talked about that. Track and collect is easy. We have our our tool with our needle that can be moved on top of a vial, and then we are just collecting inside the vial. I think that's nothing I need to talk about that much. It's basically sold nowadays when people want to do GC times GCMS, because these vials then can be dedicatedly put on another instrument for GC times GC analytics. That's the way most of our customers that have GC times GC are working. Okay, that's this presentation. Do you want to have a quick break?
Sure.
Yeah. explore or explain how epoxidation works. Most of the slides you already know, but I just want to give you more information here. We have already seen this example and why we need epoxidation, because unsaturated hydrocarbons like beta-carotene are eluted in our Mohr fraction. And one idea is to remove them by transforming in epoxides, because they can be removed by HPLC. The idea is aromatic hydrocarbons are not affected, which is not 100% true, but to a very high extent. Basically, it's not only for Mohr, it's also for MOSH. I was already telling you that monounsaturates, so compounds like that one here from ginger, for instance, are in the MOSH fraction, although they are not MOSH. It's terpenic compounds from the spices or the herbs, while we have in most vegetable oils some kind of multiple unsaturated compounds like beta-carotene and quite a few more. But it's always coming to this reaction here. We have a per acid. So this is an acid with two O's in here. And we have this reaction mechanism via this transition state forming from here to here. Okay, so far so good. With the idea that epoxides are retained on the silica column, because with the oxygen they are much polarer, or they are much more polar than before, while this is not retained or is eluted in Mohr, this is eluted at a higher retention time. MCPBA, which is typically used in the lab. During organic chemistry, you typically do all epoxidations with MCPBA, because you can just buy it. It is stable, it is safe. And for organic chemistry in labs, it's normally the reagent you are using. For Mohr, unfortunately, it has a few issues. Because first of all, what I was explaining, it has quite a few impurities, which means there's compounds inside in the MCPBA that can disturb your Mohr chromatogram, because of these are just in this chemical compound. During the synthesis of MCPBA, as you can imagine, there is unfortunately already a benzene ring. When you cut off this part, and maybe also the chlorine, but even with chlorine, these compounds are all eluted in the Mohr chromatogram. Can be forming distinct peaks. Depending on the amount, can also form clusters and little humps, and could potentially prevent quantitation of very low amounts of Mohr. It all started with epoxidation in dichloromethane. This is typically the solvent you are using during epoxidation with MCPBA. If it, of course, means that after the reaction, exactly like 1-chlorobutane, you need to remove all the dichloromethane, reconstitute against hexane to be able to inject these into the HPLC, because dichloromethane and also all chlorinated solvents need to be removed to essentially 100%. Otherwise, you get observations like we have just seen here seconds before, TBB will be too small, with the consequence that you are over quantitating. In the method till 2016, it was the case that the reaction would needed to be done in this way. During my PhD, I found out that it could be done also in ethanol. Ethanol has the advantage that after the reaction is finished, you just add water to it. Ethanol is completely separated from the hexane. You can directly inject hexane, which makes it much easier compared to the dichloromethane version. But unfortunately, one big disadvantage of epoxidation with MCPBA is that to get good results, you need to do silica gel cleanup before you are doing epoxidation. The reason for that, and unfortunately it's also difficult to automate what I pointed out already last week. You need a glass column, a lot of silica gel, and of course you can imagine it's quite complicated on the PAL to automate that, especially when you need one glass column for each sample. Why that is needed is a little bit profound in the transition state. So this one here, by the symbol, this is called a transition state. And transforming from here to here, you have this intermediate transition state. Yeah, so some kind of, this is called a butterfly transition state, because it looks a little bit like a butterfly. And this only forms in non-polar conditions. So as soon as you have some polar byproducts from a sample, this transition state cannot be formed anymore, making this reaction very slow. By silica gel cleanup, you are removing all polar compounds. So this transition state can be formed quickly, and you get a good chemistry, a good yield of epoxides. But this unfortunately is needed in case of MCPBA. Otherwise, this transition state is not forming. That's a chemistry thing. You can also just ignore it. The important part is MCPBA epoxidation needs manual silica gel cleanup. If not, you get very nasty chromatograms because not all of our biogenic compounds can be transformed to epoxides. Luckily, this is not needed when we are doing performic acid epoxidation. Performic acid epoxidation is not named performic because it is some kind of performance or something like that. It's formic acid in form of a per acid. So this is called performic acid. It's not performance. But in fact, it has a few advantages. The very first one, it was basically the main reason why I started all of that, because I wanted to find something that doesn't need to be cleaned up anymore, like MCPBA. Because both compounds, so formic acid and also hydrogen peroxide, are not soluble in hexane. There is essentially a very, very, very low chance to be contaminated with mosh or moa. Therefore, we do not need to clean them. Up to now, I have not seen any mosh moa contamination coming from those two chemicals. So therefore, essentially free of mosh moa. Both compounds are stable, so by themselves, formic acid and also hydrogen peroxide is not a big thing, especially also hydrogen peroxide. The one we are using here with 30% is coming in a stabilized way. So there's some stabilizer inside that should minimize the decomposition, and by itself it is stable. It has, which was a nice by effect, that it has a better efficiency when it comes to epoxidation, which means we have less compounds in the chromatogram that disturb quantitation. And as a very nice second effect is that it doesn't need silica gel cleanup before. Not sure why this is needed. This is not needed, but that's the general observation. The formation of performic acid is catalyzed by high concentration of H+ ions, so highly acidic conditions. That's why we are adding 10% phosphoric acid. That's basically the catalyst that accelerates the formation of performic acid from these two chemicals. It's basically 90% formic acid, 10% phosphoric acid. That's why we pre-mix this in one vial and have hydrogen peroxide in the second one. As soon as you would put them together, you would have performic acid, which is not stable over time. Performic acid decomposes by itself into CO2 and O2. This is what we are seeing in the vials during epoxidation, creating the high pressure, also deforming our septa. Why we need this special syringe to vent the vials. So you cannot premix everything. You just can put two things in two separate containers, and you are putting them into a sample, which is called then an in situ formation of performic acid. And just to compare every method that was available on the market, that was a palm olein I had during this time. This is part of the publication I did in 2021. Just ignore this part here. But for now, we have the three methods that were available during that time. DGF method, that's a German local method that was using ethanolic MCPBA epoxidation. EN 16995, that was MCPBA and dichloromethane. And this one was doing this time performic acid in hexane without a chlorinated solvent. So just N-hexane, performic acid into it, and to compare. And you can see that even in this stage, the black chromatogram looks much cleaner than these. Because what we are seeing here, these of course are all Moa chromatograms. But all this stuff here is not Moa, it is biogenic interferences. For completeness, I put the mosh hump in this trace here. You can see none of these shapes looks like that one here, which is also, as we have learned last week, a good indicator that it's probably not all Moa what we are seeing here. This shape is perfectly Gaussian, while this one looks very ugly. We take now this chromatogram and we zoom into it. So the black one is still this one here, but you're seeing that there is still stuff in there. And then this was during the time when I started with chloroform. You see that the red trace is even cleaner compared to the black trace. When you look on the shape, the red trace looks more or less like the shape for mosh. This is why we are nowadays using a chlorinated solvent, during epoxidation, because in many cases, depends a little bit on the matrix, it's giving you better epoxidation efficiency, so that the hump shape is easier to see. Because in the black version, you need to decide by yourself. Do you cut from integration this part here on top? How much do you cut in this area here? And it got easier in the red version. Of course, I know that's a very nice example. We will have 10 other samples that look completely different. But up to now, epoxidation in a chlorinated solvent is giving the highest confidence. Of course, I cannot guarantee that it works for all samples. That's perfectly fine. But it's giving the highest degree of confidence. That's why we are using performic acid in chlorobutane, because chloroform, as you know, is carcinogenic. Therefore, people complained about that, and I needed to find another chlorinated solvent, and chlorobutane was an easy choice that has also other advantages, but this is part of another slide show later.
Sorry.
Yeah.
When I first, if I don't know, you never explained to me all this, right?
Yeah.
When I first look at this, my first thought would be, are you losing more? Because it's like very flat. So your argument or your analysis, because for the mosh peak, it doesn't coincide with.
Yeah. In fact, it's basically that.
It's two humps.
It's basically at least two humps what you're seeing there, and then it comes back a little bit to experience. When you are analyzing multiple palm oleins or palm fats, you will see this cluster in all type of the chromatograms, even when when mosh is at a totally different time. So this cluster is very typical for palm oil samples.
Oh, okay.
Because these are compounds that are present, of course, not only in palm oil, but during refining of palm oil, these are more or less always
These are biogenic stuff.
Yeah, this is all biogenic stuff. This is all biogenic stuff, but you are absolutely right in asking how can I be sure to not use more? I just cannot.
But this is based on experience because
Yeah.
of palm. These are
Yeah.
biogenic. You know
Yeah.
this about. Okay.
So the top all is the MOA. All the top is a MOA.
This is all this is all MOA. Only this is mosh. Therefore, I just put mosh here. This is MOA, and these are 3 MOAs of the same sample. Just another sample prep. Yeah. Therefore, because of all these things, we nowadays use performic acid in chlorobutane.
Just curious, if you align those blue and green with the mosh, it doesn't align. Do they align to the repeaters of retention time and the?
You mean when you only look on this
Yeah.
area here? I would say they align, but only by coincidence, unfortunately.
Hence we will over report, right?
Yeah, but not only a little bit. As you see, also this is here. So as I said, this trace is this one here in black. So this is 1.8, which is fine. It's below 2. But you can imagine when you just integrate all of that, you will be probably in the range of 4 or 5 milligrams per kilogram. Yeah, so that's unfortunately experience. Sometimes you need to analyze multiple samples of the same matrix to get this experience, to see how biogenic interferences look like. And nowadays, when people have enough money, they are putting such samples into GCMS or GC times GCMS. Even in GCMS, when you would click into this cluster here, you will see this is biogenic compounds. You cannot see if there are aromatic compounds in there, but you easily see that this is biogenic nature, which is again giving you some more information and, as I said, to a much cheaper price than GC times GC. GC times GC, in fact, allows for many of those samples that this area here then is spread in the second dimension to another spot. Then you could quantitate by GC times GC FID.
We go back 2 or 3 slides on the MDBA preparations. I recall when we looked to ISO document, they also mentioned there's a possibility of purifying this. Does it help to prevent? Then forget it. Let it carry on.
Okay. Up to here, everything understood?
So even purify the chromatogram still cheap.
Yeah. You mean basically now for MCPBA? Yeah. So therefore, I would not recommend anybody to use MCPBA anymore, because it has clear disadvantage when it comes to these questions here. Initially, that many people forgot when they took MCPBA in ethanol. When you look into my publication from 2016, this method I designed specifically for minimal loss of MOA. Minimal loss of MOA, unfortunately, also means less removal of biogenic compounds. As I said, a specific method is never 100% specific. And unfortunately, it means when you want to have a better removal of biogenic compounds, you need to live with the fact that you are also losing to some extent MOA. You cannot decide between both. Therefore, the MCPBA method from the beginning, and that's what many people just forget, is it was designed to prevent as much MOA as possible. Therefore, it means it's the perfect method for easy matrices, because it will basically do not lose much MOA, but it's not suited for complicated matrices. Therefore, my recommendation today is use the performing acid method in an halogenated solvent like chlorobutane. And when all people are doing it in a comparable way, this is what we see in ring trials. At least we get comparable results. We need to live with losses of, let's say, 20-25% or more. Depends a little bit on the refining state of the mineral oil, which is in the contamination. When it's a highly refined mineral oil, like Gravex, we lose nothing. That's funny, when you are doing these tests in Gravex, you see 0% loss because it cannot be epoxidized or oxidized. When you do the same test, for instance, on the SN500 oil or the Omala, which I brought here, we're losing around 30% because this is compounds inside that in the end might even be carcinogenic. And unfortunately, carcinogenicity sometimes is related to chemical activity, which means these compounds can react with a per acid. It's unfortunately something you cannot completely separate from each other. But therefore, when we looked on the second day on the recoveries that are allowed, therefore we have now 70% recovery, which is perfectly fine. But comes down all to these facts here. Just this is an interesting one because this was a ring trial sample, a coconut, refined coconut, which was spiked with a very crude mineral oil. So high amount of 3 to 7 ring pHs that potentially could be carcinogenic, but that's not important in this stage. Let's just have a look on the blue trace. Is epoxidation after when it is done in hexane. The gray one is epoxidized in chloroform, and you see this is now a loss of around 30 to 40%. Because epoxidation in chloroform is much more effective than in hexane. This was the very first version of my method. During this time, I didn't know that chloroform, unfortunately, by itself can react also with hydrogen peroxide. Now, again, very chemically, chloroform by hydrogen peroxide can form chlorine, so elemental chlorine. Elemental chlorine, unfortunately, can chlorinate benzene compounds like perylene, and these again can be oxidized by hydrogen peroxide. You see the same compounds and the same peaks as you would have been seen when you have not installed EDTA trap in a Shimatsu pump. By GCMS, these peaks you are seeing here, it's that, and also this small one here. This is chlorinated perylene, which is then again also chlorinated by our chloroform. That's something you don't need to think about anymore because in chlorobutane, it's not possible anymore. So this was one of the side effects when using chloroform because it allowed some side reactions that were unintended. But only to show you, that comes to your question, when you would just look onto this hum, you think it's perfectly fine. Only when you do a check in another solvent, you see that this hump normally should be much bigger. So therefore, unfortunately, it's not this easy to answer if you have lost more or not. There's no general rule of thumb how you can be sure. What I only can say is that in chlorobutane and hexane, both of them give you more or less the same amount of losses, with the advantage of chlorobutane and even more effective to remove biogenic compounds. Okay.
The blue color is
That's the same sample.
Blue color is pearline. Without the iron.
No. This is MOA here, of course. This is Parylene from the internal standard.
Black color is.
Black color, that's yeah.
Meaning chloroform.
One
Higher side reaction. You see the CL they are more side reaction because of more correlated aromatic. Just internal standard is reaction. So they are higher side reaction.
Why more side reactions than the
they form the hormone.
Because you are forming chlorine.
so you are losing more
Because chlorine, unfortunately, is very active, of course. Can be chlorinating your Parylene. That's these peaks you are seeing here that are not present in the blue chromatogram. This is chlorinated. This is chlorinated Parylene. Because we have formed chlorine. That this is again, when we talk about selectivity, sometimes chemistry is doing stuff you just don't expect. But when you think about it, then you come up to this, and it makes totally sense. This was also one of the things why chlorobutane is much more attractive, because it cannot form chlorine from this stage.
so because of chloroform I'm using my more.
Not directly by chloroform, it's by the chlorine formed from chloroform.
That's why my heart is smaller.
Yeah. Exactly.
It's not necessarily happen to Parylene, it can happen to other aromatics in the MOA also.
Yeah, this is what you're seeing here. The hump is much smaller than it should be, because to an unknown extent, the same side reaction can happen to some more and some not. When we would do the same test in Grabex, you don't see any difference between hexane and chloroform. But for this specific oil that proof ACS spiked into, this is a crude mineral oil. So a crude mineral oil prior to all the refining stages, still containing a high amount of carcinogenic compounds.
This is actually a very good data to fight with a competitor.
In fact, this is a very bad example.
I mean, let's say competitors still promoting or they will not. Is it?
As I said, chloroform is not allowed to be offered by anybody, only by us. In fact, a good comparison would be this one. This was one of the very bad examples, because we have seen that people using the automated workflow in this proficiency trial measured lower MOA amounts than people using then other methods. And then
so push customer to use chlorobutane compared to chloro.
In fact, we have also fixed that already with the chloroform method, because what can you do to minimize this side this reaction? You can either change chloroform to another solvent, but you can also do, when you are minimizing the amount of hydrogen peroxide, this will do the same. And you might know that in the very beginning, when we started the automated workflow, we sold the instrument, or the method was using 400 microliters of hydrogen peroxide. After we found out, we lowered that to only 200 microliters, fixing everything. So in fact, I already fixed that with chloroform, but because, as I said, chloroform carcinogenic and people don't want to have it in the lab, it's even better to change to chlorobutane, because then we have essentially fixed it on two ends.
To lower the H2O2 also.
That's chemistry, unfortunately.
So have you did the studies on after changing in terms of lowering the peroxide amount and even chlorobutane, what's your losses?
Not worse compared to hexane. So the chromatograms then basically look the same. which was the goal. It doesn't make much sense to have a method that's much more aggressive and is losing much more because people were not accepting that. So basically with chlorobutane, it looks basically the same.
So hexane is about 20% based on experience.
Depends, as I said, depends on the mineral oil. Depends highly on the mineral oil. I would say in the range of up to 30%. But again, the more refined the mineral oil is, the less are the expected losses. When you have unrefined or crude mineral oil, let's say 30%, more or less. That's unfortunately chemistry.
So when we design experiment for, let's say, pre-sale sample analysis, we need to be very clear what customer is doing and then do what kind of spiking experiment to prove that, right?
When you really want to be sure, yes. But nowadays, I would say with this fixed method protocol, and we are now using chlorobutane since I think already more than a year, 1.5 years. I think we switched to that in the beginning of 2025. At least we did not get any complaints anymore.
No, I mean not because of your method. Right? I mean like because different standards behave differently.
Yes,
so like
true.
Max, I will always get 100%.
True.
Even I do epoxidation.
Yeah.
100%.
True.
So whatever sample analysis I just spike with Max, I will get the same fantastic
Absolutely.
result.
Yeah. As I said, this is in the beginning, and I think even nowadays labs are still using Gravex because of all the advantages. It gives you.
If I do the Shell SN, what?
500, SN 500.
Yeah, very bad coverage.
I think SN 500 is lost to 20% maybe. Yep. And then, unfortunately, it comes also into play. You might know, although we have removed during saponification most of the matrix out of our sample, we of course have still polar constituents like, for instance, tocopherols, fatty alcohols, sterols, and other type of compounds. These products, of course, independent of their concentration, also affect to some extent the kinetics during epoxidation of MOA, which means when you do a spiking of SN 500 into olive oil, you could get another recovery than SN 500 in palm oil.
Because of the matrix. But it drawbacks the machine.
I'm just curious, is this a common practice now since you all know about this? Like different region of the air, more right, will have slight different losses. Then why can we just apply a correction factor? We say, okay, the unrefined region, right? 70%, so I apply a correction factor.
Not so easy, unfortunately, because just by the boiling point, you cannot decide how high the correction factor needs to be. From the shape or from the final chromatogram, you cannot decide, you cannot see, you have no choice, you have no idea how to find out how many is lost. The only thing you could do, for instance, is doing epoxidation, for instance, with a shorter period of time. When you do epoxidation not for 20 minutes, but for 10 minutes, and you get out of the sun a much higher hump, of course, you will also see more biogenic compounds. But that is honestly the only option how to find out.
I see. Oh, so you play with the epoxidation time.
You can, but honestly,
then you have an idea how much is it really losing during.
This is at least a way how to find out. But honestly, I do not know any customer who has tried that because they just are not interested. That's also something I have discovered in the last years. People are expecting 100% perfect method, and they blame always me when it is not giving perfect results. I have got so many samples also from this area of the world, that I needed to analyze by myself in Germany because people were not getting the results they were expecting. You might now ask, how do they know what to expect? Yeah, it's because they are sending the samples to some contract lab.
So they thought that contract lab result is perfect.
Sure. Sure.
Same concept in Asia. Same, you also think the
Yeah, I have so many palm oils and other kind of stuff from Malaysia, Indonesia. I think not so much from Singapore, to be honest. But it's basically made Malaysia and Indonesia. It's, as I would say, in many cases, some kind of a palm fat. Could be RBD, could be palm olein, whatever. That I needed to check to get my results to see if they are the same as on the customer side. Then you can imagine that it gets complicated because you have the customer that is only having a report from the contract lab with a few numbers on it. Then I'm telling them, okay, you need to get the chromatograms because without chromatograms, no, you are forced in a contract lab because of ISO, blah, 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 blah. When you ask them, they are forced to give you the chromatograms. For all. Of course, by themselves, they are not supplying it, but they are forced when they are accredited according to ISO, I don't know the number, and you ask them, they need to give you the chromatograms. And only when you have chromatograms, you can compare one to the other what really happened there. Because when the chromatograms by the naked eye look completely different, you can be pretty sure that there is some bigger mistake. And even contract labs, even when they are accredited and whatever, of course, also they do mistakes. That's normal. But that's sometimes difficult to explain. We have already seen that, so I skip that. It's just where our chemicals are. For MCPBA, we have seen that before, that's exactly the same. And we are now here because that is a statement from the ISO method, how to clean up MCPBA. So that's the copy of the statement. It's effectively, it's a little bit more complicated than needed. But in fact, I put it also here in a recommendation that you take a clean beaker, wash MCPBA in hexane multiple times, and you leave it drying maybe overnight or something like that to wash out everything that might be elutable in the MOSH or the MOA chromatogram. You can see when you look into this part here, they're telling you need to have a special PET container, then you need to do ultrasonic bath, then you should filter by a vacuum frit. You can do it perfectly fine, but it's faster and easier when you just have a beaker, put your MCPBA inside, multiple times, hexane on top, decant as most as you can, and leave it in the fume hood overnight. In the next morning, you could potentially put it back also in the container where it is delivered from. But you need to be careful because the container is made of PE, which means do not put much solvent inside because you will extract POSH out of the container. So in case you have a customer that is still using the MCPBA method, that would be the recommended way to clean the chemical. Not that complicated, but for the performing acid, you do not need to think about anything.
So MCPBA is not dissolved in hexane.
Exactly.
So you clean it, and then when you're doing this cleaning, you will remove the 20% water.
No, because water is also not soluble in
So it's still
hexane.
stable.
It's only important you should not try to use something which is mixable with the 20% water inside. Because then you are removing all of the water. Then you have 100% pure MCPBA, and that can be shock sensitive. So therefore, safest way only hexane because then you are always on the safe side. You can even throw it against some wall. Nothing will be shocking or whatever. Just very briefly, because we will do that also later in practice. After epoxidation is done, it's now for ethanolic epoxidation, but for performic epoxidation, it's basically the same. You have something like a sample transfer penetration, which means you need to find out, we'll do this later on the instrument, how deep the needle can penetrate into the vial, because obviously you do not want to transfer the lower layer. I think that's self-explanatory. For the automated workflow, unfortunately, these are a few more penetration depths, but again, the same principle. In fact, it is after saponification you have, because we're doing it twice, 2 penetration depths. Then after epoxidation, which is the third one, and after liquid partitioning in the final vial, so we have in some 4 penetration depths. The good thing is, as long as the layer separation is at the same height, this works all the time. Becomes critical or needs to be adapted as soon as you start to change the amount of sample. So when you go to spices or infant formula or let's say rice, and you would want to analyze that, the sample penetration needs to be adapted. Just for your information, up to now, I'm not finished with that, but I'm pretty confident. I cannot say in the near future, but I hope in the not so far future, there will also be an AI-guided automated liquid layer check from us.
By camera.
By camera.
It's not from CTC, right?
No. We need to do that, or basically I need to do that by myself.
So next time, this small parameter will be removed.
As I said, it's not in the very near future, but I hope that it's not so far away. So it's basically just by camera detection that the camera tries to find the layer separation. When you know where the layer separation is, it's basically easy to know how deep the needle can penetrate. Yeah. But as I said, not for now. Okay, that's this. Any questions about epoxidation at this stage?
So now you're only working with 20 mil balls, right?
Yeah.
Even though your system doesn't have automated workflow, it's only MCPB.
We switched everything to 20 mil. So yeah, for the older instruments, we had everything done in 10 mil. But to not confuse anybody, I decided to change everything to 20 mil, because it's then easier to switch between the methods. Because when you still want to use 10 milliliter mil, the consequence is you need special adapters inside the agitator that need to be removed manually. You need to use other positions in the centrifuge, and I found it easier when we just do everything in 20 mil, because there's no advantage or disadvantage, so to say, when switching to 10 mil. I know that in the beginning we just took 10, but it works because of the long needle we have now, which we had not in the beginning. We can work also perfectly fine in a 20 mil vial.
So let's say if my customer is having two systems, one is the older one is the new one, can I, if customer asks whether they want to change the 10 mil one to 20 mil ones, can they do that?
They can, but they need to change the syringe. So you need to take then the 5 milliliter syringe, because this has the long needle, then it's fine.
In terms of the methods, we just need to check the penetration.
No, you need also another method, because we changed, I think, a few parameters. Also, the ability to use sodium metabisulfite. To use that needs a slight change in the method. So when you have this case, give us a mail or whatever, and we will send you the method. Or to be honest, you have the method right now because it is on the SharePoint.
Okay.
because it's a little bit different to the one we developed in 2020 with the 2.5 milliliter syringe, because this had only a short needle. It was only a 2.5 milliliter syringe, and now we are doing everything with a 5 milliliter syringe and the long needle. There were a few things improved over the time. So the method is on the SharePoint, and if the customer is interested, also the 120 meter PAL can be upgraded to the 20 milliliter method, effectively just by using the new syringe. That's all. Okay. What's time telling us? So at least we have half an hour to get everything out of the instrument. Let's see how fast you are to get it back into the instrument. Now, since we do not need to measure anything today or tonight, it's fine even when the columns stay out of the system until tomorrow. That's perfectly fine.
No, I shouldn't even.
But yeah, you can turn off the gases and also temperatures on the FID.
So this on the FID temperature to down. FID temperature is okay.
Depends on how much you are used to your fingers. Yeah, so when you can withstand also 350 degrees.
You need to put
Then we put it 400. Then we do what?
Peter to what?
for SPL 那边 temperature 等一下。
对，这个也可以落到这个的低。
我都买定数题，but what about the
the 低了。
You do at the problem.
And then